So, hello everyone, and welcome to the 9th Visual Object Tracking Challenge, VOT 2021. So, I'm Miri Matas, and I'll be chairing the first session. On the first slide, we list all the organizing committee members of the VOT Challenge. It's a long list, it's a lot of work. For those who really want to read the whole list, the slides as the presentations of all the other talks will be uploaded to the VOT website as well as on the ICCV link. So I'll start briefly by recapping the VOT mission. So VOT initiative has been active since 2013, February, with the goal of establishing standards and development of trackers and development of the tracking as a discipline. The VOT provides 4 important assets. It's an evaluation system which allows researchers to get their system benchmarked or tracking algorithm benchmarked very quickly. It maintains a set of data sets which we think are diverse and useful for giving feedback to the users of the algorithms as well to the authors. We develop evaluation methodology so that the methodology reveals really the strongest trackers from the perspective of applications and further research. And we work hard on building the community where it's important that we get feedback from the community and that we develop common understanding of what the problems in discipline are. In 2021, the VOT committee has run 4 challenges. That's 1 less than last time. We dropped the thermal one. We are trying to balance between having enough specific challenges that covers different aspects of tracking and being too broad and, let's say, difficult to navigate. So let's say the core and this is the VOT's short-term tracking challenge. By short-term, we mean methods that do not have to detect occlusion and the absence of the object in the field of view. The real-time focus is on the speed aspect, and it's a reaction to let's say past trend of the winners being not really practical but due to their slow response times, which has gone better, maybe even because we introduced this real-time tracker. We have the fairly novel long-term tracking challenge where we deal with redetection, so that's going toward tracking and detection, and the RGBD, since in many cases the depth channel is available. The participation is really easy. So for those who are in the audience and have not yet participated in the evaluation of their tracker, it's enough to provide raw results in some reasonable tracker description and source code, and you get back the evaluation provided by the committee. You only have to download the data set, and more or less the toolkit automatically performs most of the stuff that you have to do. And for those who have good results, they become co-authors of the paper that is produced as the final outcome of the challenge. So focusing now on the timetable of today's workshop, we'll start with a session where the challenge results will be presented, and questions and answers sessions will follow, first by short-term and real-time tracking challenge that will be presented by Martin Kristan. Then we'll talk about long-term, presented by Young-Jin Chang. And finally, Joni Kristen Kamerainen will talk about RGBD. Then we'll have a short break, and we'll come back with the session chaired by Roman Pflufelder that will have Horace Ben-Shitrit, Second Spectrum, a company doing very impressive work in the area of sports analysis and tracking, and we'll see the huge progress in the field and the practicality of the algorithms that we develop or they develop. And that will be followed by 3 contributed presentations of original papers. In the final session, chaired by Aleš, the winners will present their algorithms so that we understand what made them so good. And in the feedback session, which will be chaired again, probably by me because Michael had some health issues, we'll talk about all aspects that you wish as audience to bring up with respect to the VOT challenges and the activities of the organizing committee, like possible suggestions of improvements of the challenge, further directions, maybe what we should encourage and so on. So we would really love to see broad participation in this part. So that's enough for the intro. You can ask questions in the chat. I will be monitoring it. Probably most of the members of the VOT committee will be looking at it and will relate the questions to the speaker. The sessions are recorded and will be uploaded to the ICCV webpage and on the VOT page. So without further ado, I will hand over to Matej, who will present the results of the short-term and real-time challenges. Matej, the floor is yours. Thank you.
Okay, thank you, Jerzy. So good morning, good afternoon, and good evening to everyone. In the next 20 minutes or so, I'll present the results of 2 of the VOT challenges, the VOT short-term tracking challenge and the real-time tracking challenge. So first, I'll briefly overview the 2 challenges, then we'll look into the results, and finally, we'll announce the winners of the 2 challenges. So first, the overview. Now, the first of the 2 challenges is the VOT short-term tracking challenge. This is the longest standing tracking challenge that we have been organizing in VOT. It considers short-term trackers that track single target with are causal trackers and that provide target localization in form of a segmentation mask. This last part, the segmentation output, was added last year. Before that, the short-term tracking challenge required bounding box as the target localization output. So the trackers in this challenge are initialized in the first frame by a segmentation mask, and then the tracker is required to report the segmentation mask for all of the remaining frames in the sequence. The purpose of this challenge is to promote trackers that would track for as long as possible, which means that the target is always within the field of view, and any drifting of the target is considered a failure. So in this challenge, the trackers are evaluated using the anchor-based evaluation protocol. This is the protocol introduced last year. Essentially, this means that the tracker is initialized at various points along the sequence, and each initialization point produces a subsequence. So this means that the tracker is evaluated many times over the same sequence. So each subsequence, at each frame of each subsequence, we compute the performance on that frame as the intersection over union between the ground truth segmentation mask and the segmentation mask produced by the tracker. We measure 2 basic performance properties of trackers, which are accuracy and robustness. The accuracy is computed as the average overlap over the successful periods of tracking, whereas the robustness indicates the extent of successfully tracked parts of the subsequences. And the 2 measures are combined into a single performance measure, the expected average overlap. And this is the measure along which all of the trackers are ranked in the end, and the winner of the challenge is decided based on this performance measure. The trackers were evaluated on the VOT short-term tracking 2021 dataset. This dataset is actually composed of two parts, the public part and the hidden part, the sequestered dataset. So the participants of the challenge, they would run their trackers on the public dataset, and then we identify, based on the expected average overlap, we identify the top 5 performers from this dataset, and these top 5 performers are rerun by the VOT committee on the hidden dataset, and the winner is then identified as the top performer on the hidden dataset. So each of these 2 datasets contains 60 sequences. We've actually built this dataset by taking the dataset from last year and then refreshed it. So we've replaced 10% of the least challenging sequences, or sequences that were in some way duplicating properties of other sequences in the datasets. So all of these new sequences were manually segmented and were also annotated. So each frame in the sequence is annotated by the VOT attributes, the standard attributes that we have been using for the last 9 years: occlusion, illumination change, object motion, object size change, camera motion, and if there's no property particular that can be assigned to the particular frame, we set it to unassigned. Okay, so this is the short-term tracking challenge. And now about the real-time tracking challenge. The real-time tracking challenge is very much the same as the VOT short-term tracking challenge. So it uses the same data set and the same performance evaluation protocol. The main difference is that the trackers are required to process frames at 20 frames per second. So this means that the toolkit will wait for the tracker response for at a rate of 20 frames per second. And if the tracker does not report the result in the prescribed time, the toolkit will ignore that result and provide the next frame. In this challenge, the winner is identified on the public dataset. And as Jiří said before in the introduction, this challenge was introduced some years ago in 2017 to promote efficient architectures in trackers. So to promote speed as well as accuracy and robustness. Okay, so now let's look at the challenge results. Now, in the 2 challenges, we evaluated 53 trackers. Over 60% of the trackers were reporting target location as in form of segmentation mask, while the other trackers were still reporting location in form of a bounding box. Vast majority of the trackers was categorized as short-term trackers, so either short-term level 0 or short-term level 1 trackers. The difference between these 2 classes is that the short-term level 1 set of trackers would not update the visual model constantly, but would restrain from adaptation in cases where they would think the target is poorly visible or for some other reason. In terms of architecture, nearly all of the tested trackers were deep trackers. The dominant methodologies, as in previous years, were discriminative correlation filters and Siamese trackers. And we've observed the emergence of a new methodology in visual object tracking, and these are the transformers. So transformers are, in general, the emerging methodology in a wider field of computer vision, and it seems that it already spilled over into tracking. Okay, so now let's look at the results on the public data set. Here are all the trackers ranked with respect to the average expected overlap on the public data set. Here we indicate the top 10 trackers on this data set. All of these trackers are deep learning trackers. They include the winner from last year and 2 extensions of the winner, while 7 of the other trackers are based on transformers. This means that they're fully transformer or just part of the tracker is implemented as a transformer. All of these trackers report target location in form of segmentation. It's interesting to observe that 5 of these top trackers are actually two-stage trackers. So they would localize the target as a bounding box, and then they would apply a segmentation within this bounding box. And for that, they would use AlphaRef, which is the winner of last year's real-time tracking challenge. And 3 of the trackers among the top 10 were actually applying transformer architecture for segmentation. Okay, so looking into a little bit of more details, we can look the trackers, how they perform in terms of robustness and accuracy. So we see that the trackers that are top in expected average overlap are excelling both in robustness as well as accuracy. So they would track the targets really for really long duration throughout the sequence, and they would be segmenting the target quite well. Per attribute analysis shows that similar to last year, the occlusion seems to be the most challenging attribute. Occlusion is apparently causing most of the failures and is also the major reason for a reduction in segmentation accuracy. Now, to put these results in a little bit of broader historical perspective, we've looked at the trackers that used to be considered strong baselines or even state-of-the-art like 2 years ago. And we see that these trackers are already positioned at the tail of this ranking list. So this indicates really strong submissions that we received this year. Some of the submitted trackers have been published. These ones with these gray dots were published at major conferences and journals. And we typically average the performance of these trackers, and this constitutes the VOT published state-of-the-art bound. And we see that over half of the trackers exceed this bound, which further confirms that they're highly competitive trackers. It's also nice to see that 9 of the submitted trackers outperformed the winner of last year's VOT short-term tracking challenge. Now, if we look at the reason for increased expected average overlap, we have to look a little bit into detailed analysis. So this is given to us by looking at robustness and accuracy. So in this graph, I'm now showing the winner from last year, the top performer on public data sets over here. And for reference, I'm showing here a milestone tracker, Atom. So this is a tracker proposed, I think, like 2 years ago or so. And it's been a tipping point in tracking. It introduced some concepts which are used in a lot of the trackers that have been submitted to the challenge over the last few years. And we see that from the point of application of Atom, the trackers have improved in robustness as well as in accuracy. So the trackers, let's say the RPT last year and RPT mask this year, so they're able to track the target longer, and they've improved the accuracy of localization. So this was a bounding box tracker, and these are segmentation trackers. Now, if we compare the top performer from this year with the winner from last year, we see that the major improvement comes from the increased accuracy. So this means that the RPT mask is better at segmenting the target, while it's approximately the same in terms of robustness to the last year's winner. And we can visualize this with tracking of Bolt here in this sequence. So I'll just run this. So here you see the bounding box tracker has problems with confusing the target with neighboring targets. Last year's winner is much better. It sticks to the target, it segments it out, but oftentimes you'd see some spurious artifacts around the target. So the segmentation is not that great. I mean, it's very good, but not very precise. whereas this year's top performer has substantially improved that. So the segmentation is much better. Now, obviously, we're not there yet, right? So the major problem is still robustness. So trackers tend to fail in very challenging situations like high clutter, something that we see here, or major occlusions, things like that. So it would be really nice to see in the following years these graphs over here to be pushed towards the right. So to increase the robustness, to try to stick to the target for a longer duration and maybe somehow recover from local failures in the sequence. Okay, so as I said, on the short-term tracking challenge, the top performers, the 5 of the top performers were rerun on the hidden data set. And here I'm showing the results of those trackers on the public data set and on the sequestered, on the hidden data set. So what we observe is that the performance of all of the trackers drops on the hidden data set. The drop is non-negligible, but if we look at the top performer on the public data set, we see that it stays ranked #1 on the hidden data set as well. So despite the substantial performance drop, the ranking is stable for this tracker. So it's also top performer on the sequestered data set. Okay, so here we're showing now all these trackers re-ranked with respect to the expected average overlap computed on the real-time challenge. Here's the top 10 performers on the real-time challenge. This is the winner from last year's challenge. So it's nice to see that 7 of the top 10 trackers actually outperform the last year's winner, and nearly 1/3 of the trackers outperform the VOT real-time published state-of-the-art bound. In terms of architectures, it's also interesting to observe that 6 out of top 10 trackers, so these guys over here, are based on transformers. So this is sort of it seems like a common property of this top performing real-time trackers. It's also interesting to observe how the ranks of the trackers change between the 2 challenges, so the short-term tracking challenge and the real-time. So what we observe is that 5 of the top 7 trackers on the real-time challenge are among the top 10 trackers in the short-term tracking challenge. In fact, if we look at the top performer on the real-time challenge, we see that its performance its expected average overlap does not drop at all with the real-time constraint. So that's quite interesting. And also, we noticed that 6 of the top 7 real-time trackers, which are again, among the top 10 on the short-term tracking dataset, are based on transformers, which indicates very interesting real-time capabilities of this new methodology, apart from delivering excellent tracking performance. Okay, so to summarize, in the short-term tracking challenge, deep discriminative correlation filters and Siamese correlation networks are still the dominant methodology. We have observed a rise of a new methodology, the transformers, and usually when this happens in VOT, so we had a similar event occurring throughout our history. So usually when this happens, that a certain class of methodologies or certain class of trackers sticks out from the rest, we see a large set of variations of that methodology submitted on the next challenge. So I kind of expect a lot of exploration to be done until the next VOT in this class of trackers, and I hope the performance is going to be boosted further. It was interesting to observe that half of the top performers were actually two-stage trackers. So they would split localization and segmentation step. So for the first part, they would localize the target with a bounding box, and then they would apply the AlphaRef, the winner of the last year's real-time challenge for segmentation. And we also observed that the performance improvement this year is primarily due to segmentation accuracy. So the segmentation part of the trackers has mostly improved compared to the last year. Now, in the real-time challenge, we also observed the emergence of transformers, as I said. So they give us very good compromise between the speed and robustness and accuracy. And it's nice to see that the speed or the robustness is not sacrificed for speed and vice versa in these trackers. Okay, so now it's time to announce the winners. So the winners of the short-term 2021 tracking challenge are, and I'm just going to go ahead and apologize for butchering your surnames, guys, but here goes. The winners are the authors of RPT Mask Tracker. These are Zhihong Fu, Liang Wang, Kili Deng, Kang Du, Kyungji Liu, Yunghong Wang. Okay, so great job, guys. Congratulations on a very interesting tracker. Now, the winners of the real-time tracking challenge this year are the authors of the TransTM tracker. These are Jin Chen, Jiawen Zhu, Bin Yan, Dong Wang, Huchuan Lu, and Xiaoyong Yang. Okay, also congratulations to you guys as well. We've sent to you guys the winner plaques as well as the VOT t-shirts, which have been printed again in limited edition due to the online nature of this event. So the t-shirts again are the VOT collectible item, which were printed only for the winners and the VOT committee. And to the audience, stay with us, and in session 3 of today's workshop, you will be able to hear from the winners of these 2 challenges about their trackers. They will describe how they designed the trackers and what makes these trackers so great. So finally, I'd like to thank the VOT committee for putting extra effort into running these challenges and evaluation. I'd also like to thank everyone who participated and contributed to the challenge. Thanks for submitting such cool trackers. And lastly, I'd like to thank the sponsor, University of Ljubljana, the Faculty of Computer and Information Science, that was financing the t-shirt printing. So yeah, thanks.
Okay, thank you, Matej. We have a few minutes for questions and answers. From my point of view, the presentation was crystal clear. It's clear that you are not doing it the first time. Interesting results. So any questions from the audience? There's nothing in the chat, so please go ahead. Okay, so while there is no question, I'll ask one. I think that the difference between the performance on the sequester dataset and the standard dataset is quite large this year. It almost seems to me a little bit larger than it used to be. Do we suspect that our dataset, the sequester dataset, is more difficult, or there is like a higher level of overfitting, but even some of those methods, like the transformers, were performing better? So maybe so any comments on this or ideas? Yeah, so overfitting is always present. You can't avoid it. I mean, it's a challenge, and you want to score the best as possible. This is something that we always see also in scientific papers, right? So the authors always try to come up with best set of parameters and best tweaks that work best on those data sets. This is something that we've been trying to
work against in VOT, right? So we said that you don't have to, you know, run for that #1 position exactly because it's easy to overfit. But I would suspect here that it's not just overfitting. Probably there's a sequence in the sequestered data set that's slightly more challenging than the equivalent sequence which is present in the public data set. So in part, you could say that this is also overfitting, but obviously probably the added sequence is more challenging. Yeah.
Okay, so thank you. There's one more question in the chat, and I actually had the same question in my mind. It's from Yoni, and if you look at the charts, at one point in time there is a jump in performance in accuracy, like the only discontinuity in this whole graph, and then so what happened at that point?
Yes, quite good observation. Thanks. Yeah, so I think I would have to check, but as I recall, this is probably the point where the trackers change from bounding box to segmentation, right? So all of these guys that I'm showing here, they produce the target location, they report it as in form of a bounding box. Now, bounding box is a very approximate segmentation. So those trackers that explicitly apply segmentation, and this was sort of introduced last year, so those trackers would perform better if they had at least equal robustness to these guys over here. So this is what happens, right? So, and you see it here in robustness accuracy. So I always like to show robustness accuracy plots combined with the expected average overlap. So this is another thing that we were always saying in VOT, that you should not look only at a single measure because it doesn't tell you much. Whereas the accuracy robustness reveals exactly what I said. So you see these trackers here below. So these are the trackers which are ranked.
Mate, we only see your last slide. We still see slide 21 of 21.
Oh, really? So,
at least I do.
So do you? What happened? Let me see. Am I sharing the screen or not?
You are, but at least I don't know. I see, and Horesh is nodding. I see slide 21 of 21.
Let me check. This is something happened with my Zoom controls. Very weird. Okay, let me. Jiří, can you take over the screen sharing from me so that so maybe the Zoom will release whatever bug it's got caught into. Okay.
Done.
Okay, so let me try sharing again. Okay, so it's, yeah, the Zoom has somehow broken for me. I can't.
Okay, doesn't matter.
But so what
leave this offline. The message is clear, and it's an interesting
so the accuracy robustness plots actually show that those trackers that are at the tail are still quite robust. They would track for long duration, but their accuracy was very low, and that reduced the expected average overlap. That was the main.
So it's in some sense it's validating our switch from bounding boxes to segmentations, and it's interesting. Yeah. Okay. Yeah. Good. Fine. So, Mate, thank you. We'll switch now to the talk on long-term tracking challenge, and it will be presented by Hyung Jim Chang. Hyung, could you please take over the screen sharing and do the presentation?
Okay. Right. Do you see my screen sharing?
Yes, we see your screen.
Okay, thank you very much. Hello, everyone. My name is Hyungjin Chang from the University of Birmingham. I'm a challenge caretaker of long-term challenge. So I'm going to overview of the challenge first, and then report the result of the challenge, and then I'm going to announce the winner of the challenge. So the overview. So this VOT-LT challenge addressed RGB tracking in a long-term tracking setup in realistic surveillance scenarios, and is a continuation of the VOT-LT 2020 challenges. And the target positions are encoded by bounding boxes, and the tracker have to determine whether the target has disappeared and redetected once it reappears. The tracker is required to report the target position in each frame, along with the score that reflects this certainty that the target is present at the position. So the challenges are robust visual model updates and building robust detectors in a large target search, in a very large target search windows, etc. So the trackers are evaluated on the LTB50 dataset, which is the same dataset we used in VOT LT20. The long-term performance evaluation protocols entails initializing the performance in the first frame and the sequence, first frame of the sequence, and running it until the end of the sequence. So this data set contains 50 challenging sequences of diverse objects, including persons, cars, motorcycles, bicycles, boats, animals, etc. And the average sequence length is 4,000 frames. Actually, it's more than 4,000 frames. And the average per sequence disappearance is more than 10 times. And the average target absence period is 50 frames. So the target position was initialized at first frame and no reset during the tracking. And the target tracking performance was measured by localization and loss or presence detection, etc. And the sequence were annotated by by these attributes, visual attributes, such as full occlusion, out of view, partial occlusion, camera motion, fast motion, scale change, aspect ratio change, visual change, viewpoint change, or similar objects, etc. And the performance is measured by two basic measures called precisions and the recalls, while the overall performance is summarized by the F1 measure, F-score measure, right? And the VOT-LT 2021 winner was identified by as follows. So the tracker were ranked according to the tracking F-score on the LTB50 dataset. The top ranked tracker on the dataset not submitted by the VOT 2021 committee members. Okay, so this is the summary of the challenge results. In total, there were 13 trackers tested. 10 out of 13 are new submissions, and we contribute 3 baseline methods. So the last year, there was 5 submissions. So it's a big jump of the submission numbers. And all trackers extracted CNN features. And we observed that like 5 trackers begin to use transformer-based network for target localization. And all trackers were from LT1 class, which means the target position is not reported in frames when the target is not visible. The target detects the tracker detects tracking failure and implements explicit target redetection. The architectures were getting more and more mixed, and most of the trackers combine many different methods and achieve high performance. Among all methods, Super DIMP, Stark, and Meta Updater are the top 3 popular methods. Among 13 trackers, super DIMP were used in 5 times, and Stark was used in 4 times, and meta updater was used in 3 times. So among the all submissions, there are we have chosen top 3 trackers, which is MLPLT, Stark LT, and Stark RGBDLT. So the MLPLT is composed of a transformer-based Stark tracker. And it is also using the Spur DIMP tracker and online learned target verifier. So Stark and Super DIMP are run parallel for target localization, and the decision strategy selects whose localization can be accepted based on the validation from the verifier. And the second was Stark LT. Stark LT architecture applies a Stark tracker based on transformer for short-term tracking, and a global search algorithm based on global track for the redetection in the whole image. Also, the baseline method we tested on our LT DSD, which is the winner of VOT-LT 2019. And we have observed that 7 trackers outperforms this baseline method. Especially the MLPLT outperforms winner of 2020 and winner of 2019 in most all the attributes. In particular, like partial occlusion, scale change, and viewpoint changes were outstanding. Okay, these are the comparison between 2020, 2019 the best winners. Still, this contains many challenges such as partial occlusion, scale changes, and viewpoint changes. And as you can see, the red is the best performing method of this year. So it's keep losing. It's it keep disappearing from the view, but as you can see, these 3 winners are well redetecting the object. But this year's the MLP gets a more high accuracy because it's a little bit more stable, and in terms of detecting and in terms of the tracking both. And this is another case for which is very challenging video. The object is very small, and there are full occlusions, and also there are fast motions. Let me skip a little bit. So as you can see here, these 3, this is very challenging because it keep appears and disappears, and the MLP LT sometimes it lost and redetect different objects. So it is still very challenging task for all. So we can summarize the challenge like this. We have observed that there was a fast performance improvement within 1 year, and also the transformer-based method is outperforming than previous years. Especially the top 3 challenge, the top performing trackers are all using transformer-based methods. And also the deep LT architectures are stabilized now and well mixed. So that's very much encouraging part. But still, the small object, fast occlusion, and fast motions are very challenging tasks remained to this year. Okay, now I'm going to announce the winner of this year. The winner goes to the MLP LT by Matteo Donhofer, Christian Simonato, and Christian Micheloni. The paper title is Fusing Complementary Trackers for Long-Term Visual Tracking. Congratulations. There will be winner talk in the session 3. Right. So as I thank you for all the committee, VOT committees and caretakers and the participants. Thank you very much.
Okay, Jan, thank you. Interesting talk. Is there any question from the audience? So far, nothing in the chat. Okay, so since we have nothing in the chat and we are perfectly on time, thank you once again, and we'll switch to the last presentation of challenge results, which will be by Joni on the RGBD results. Joni, please take over the screen and go ahead.
All right, give me a second. Now, I hope everything is visible.
Yes, it's nice. Go
All
ahead.
right, beautiful. This is the third time of RGPD challenge and tracking VOT. This time the 4 persons kind of like mainly working on this stuff was Ales, me, Song and Chinu. Most of the work, of course, I need to admit, was really Song Yan and Chinu Yang, who did a lot of that stuff, all the kind of like experiments and so on. I think that this is kind of like, which is interesting to me. When is depth really needed, and then kind of like what are the sequences that kind of like depth is very important information for tracking. So I think first we need to, let's talk about depth. So of course there is some obvious cases. These sequences are not actually, I think these sequences have been available in the normal RGB tracking datasets. But the typical case when depth is useful is, of course, when the object that you are tracking is sharing the same color with some background clutter or other objects moving the scene. Then if they kind of like have a different depth, it might be easier to follow the target properly. And another obvious case is, of course, occlusion, because when occlusion happens, it is typically somehow related to depth changes there. So as we saw from Matej's talk, occlusion is one of the big problems. So we could even draw the conclusion that moving from RGB to RGBD, that could be the kind of like solution for many of those problems there. But we wanted to study this problem a bit kind of like more in depth. So we took DIM tracker and then we decided to do a kind of like, we tried to keep everything the same for the DIM tracker, but train it with only with depth data from the scratch, only with RGB data as it is used typically, and then kind of like later combine these both branches there and see how much it benefits really from the RGBD. So this is kind of like work that we were inspired to do this stuff when we saw the kind of like the result with the RGBD tracking work so far. The problem for training depth from the scratch is, of course, that there is a huge amount of sequences available if you want to train the RGB tracker, those deep methods and so on, but they don't provide the depth channel. So this idea was, I think, actually seeded by Matej, who kind of like thought that maybe we could use the best monocular SLAM methods and generate those depth maps and then train the depth tracker using a generated depth. Here you can actually see we tested a bunch of methods for generating the depth maps, and then we found that the dense depth was actually the best method so far. There is this ORT indicator that you can see at the bottom images that goes from 0227 to 0519, which is somehow measuring whether the depth values are in the correct order in those generated maps. And then we found out that kind of like, as you can see, everything about 0.3 looks already pretty good. And these are typical values if you read those monocular depth papers, that what they report there as well. So we kind of like, this helped us to go through all those sequences and make sure that we are using the data, which is not complete crap. Now, this is interesting what we did. The one thing was that we didn't want to take this long-term tracking into account. So basically, we actually cut all our long-term sequences to short-term tracking sequences so that we would only measure the kind of like contribution of RGB and depth. And here you can see this is the list of all of sequences in the CDTP. So basically this VOT RGBD challenge dataset. And now the blue bars are actually depth only tracking F-score, and the red bars are RGB tracking only F-scores. And then we saw that this in such a way that kind of like those sequences where the RGB is clearly the best are on the left, and then we go kind of like smoothly to the right, and on the rightmost corner the depth information is the best. And then you can see those values that basically kind of like describe how much stronger is, how many times stronger is RGB or depth. I think this one is pretty interesting because now we can see that for 80% roughly of those sequences in the RGPD tracking challenge, the RGB is better. But also interestingly, for 20% of those sequences, the depth is kind of like clearly superior. And then what is nicely interesting there as well, that most of those sequences, I would say that there's no big difference whether you use the RGB or depth. And this is now, remember, using the DIM tracker, completely trained from the scratch using RGB or depth. And you need to keep in mind that actually the depth is not real depth. So this is kind of like generated depth. So I think if we would have the same amount of real depth tracking data, the numbers would be even much better for the depth tracking. We tried to kind of like identify even that what is then the type of the sequences that where the depth is very good, because I mean for RGB it is obvious that for most of the cases RGB is enough. So now you can see the 10 best sequences for the depth on top, and then 10 best sequences for RGB at the bottom, and then basically the arrow is showing which one is better, and this ratio number is telling how much better is F-score is for that. So you can see that the kind of like the F-score for the depth tracking, it's 1.5 times better to 5 times better even. But the problem is that we couldn't really identify some kind of like clear patterns when the depth is very useful there. Sometimes when we thought that the depth should be clearly superior, we found out that actually RGB is doing pretty well, and sometimes it was kind of like not completely clear why the depth is so superior there. The one clear case is of course dark scenes, because then when we have the active depth sensors, it means that kind of like they can actually provide the vision in dark places. Cool. This is also super interesting by my opinion, because if we compare them with the different attributes on those scenes, we can see that there are certain, most of the time RGB is better here. But you can see that for some scene types, for example, the dark scene, of course, when the depth is clearly better, but then some others like depth change and things like that, reflective target, the depth is better there. But the cool thing is that when you combine those both, so basically then we just took the both branches of DIM branches and we put them together, and then I think there is a clear improvement from either RGB or depth to the combining the both. So this means that there is clearly something to kind of like gain if we are using RGBD input. Good. We learned something. We should never have introduced a long-term kind of like challenge for this RGPD, because it kind of like did hide all the interesting details from there. So if we could redo everything now again, we would have introduced only short-term tracking for the RGPD. Then on top of that, I think it would be interesting to introduce depth-only kind of like track there. So basically, because that could reveal the ideas for how to use the depth for tracking, and I think that would have been super useful as well, because then we could compare the best depth-only tracker to the best RGB and the best RGPD trackers, and that could have been kind of like provide some interesting boost to depth tracking research as well. But now I will be a bit shorter on the dataset and the results and so on, because I wanted to show some of these interesting results, and all those generated depth maps and everything will be available to you, and even the method code will be available to you, so you can play yourself with those results there. We used the main dataset was once again the dataset that we collected in 2019, and partly by mistake, because we wanted to use the sequestered data this time, but we kind of like erroneously wrote to the, or I didn't check the website properly, so we said that we will use the same data set again. But we will come back to that. So blah, 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 blah. This is the same data, you know it. But then we introduced a new data set, depth track data set. It was actually published in this ICCB, so you can find the details about the data set there. The biggest change from the previous one, this supposed to be the sequestered data set of this VOT RGPD challenge, but now because mistake on the website, it is not. But we can computed all the results with the both data sets. And then if you look this, the new data set, it's in all possible ways better, kind of like a larger data set than the previous data set. But the biggest thing which is not visible here is that we found out that in our previous data set, one object type was dominating. So I think 20% or 30% of the sequences, there was boxes in the sequences. I don't know why. It was kind of like, it sounded, it was a good idea back then, but now this new data set, it's much more kind of like diverse in terms of different object types. Let's now see something about the results. Basically, we are using the long-term evaluation protocol. We are using the bounding boxes, no segmentation mask, and so on. And we calculate precision recall, so how accurately we find the object from there, and in how many frames we can correctly classify whether the object is present or not. Then we calculate this F measure mean out of those values that we use to select the winning tracker. Standard stuff. There was 4 valid entries last time, year before that, and now we had 5. So I now a typical claim would be that now I say that there was a substantial increase in the submissions this time. I hope that that will happen also next year, because now I think we have some interesting stuff coming there. And I will jump to the results. Start RGPD surprised us. It was the winner on all the precision recall and F score with this public data set. So now you can see that the first 3 methods were submitted this year. The next 3 methods are actually the best, the winning methods from the last year, and then the remaining of these 2 submissions are actually weaker than the best methods from the last year. But the more interesting thing is that now, because how do these methods perform with the new dataset, unseen dataset? And the results are here, and surprisingly, the winning method is the same. So there was no problem that we made a typo to the web page, because the same method would have won anyway. So Stark RGPD is the best one here. There is a little change. The last year, second best method, DIMP, jumps kind of like to the third position there. Other methods, this DRefine, I would say that that method is somehow overfitted to old data, because I mean there is an obvious change there when we go to the sequestered data. Also, interesting thing is that if you look at F scores, all those values, they are substantially smaller for the new dataset. So I think there is a lot of space to improve with this new dataset. Also, if we look to attribute-wise, I think Stark does very good job. It wins all other trackers on most of those attributes. So I think it is really worthwhile to listen to their talk today about that method, because there is no surprise that the winning method for RGPD tracking this year is Stark RGPD by Chang et al. I think all the authors of these methods are from Chinese, multiple Chinese universities, one university from the UK, and Microsoft. So I mean, it's a nice combination of the collaboration of company and academia, which is always nice to see. But that's it.
Okay, thank you, Joni. You are exactly on time. The full hour have just rang a second ago. So we will have, if there is no question, which I don't see anything in the chat, so still you can post the session. So now we'll have a 5-minute break, and it will be followed by the invited talk in a session chaired by Roman. So see you in 5 minutes. And I thank all the speakers and presenters in the first session, which I found quite okay, actually very enjoyable. Thank you.
Three contributors papers, and of course our invited talk. I really ask you, we have 18 minutes, so quite a long time, and I'm really encouraging everybody to ask questions. So after the presentations, we'll have some time, 5 minutes for questions. So please ask your questions in the chat. So we start, and we are very happy actually with Horesh, with his invited talk about multi-object tracking. I would like to introduce Horesh a little bit to our community. So Horesh, you are actually originally you're from Israel. I've seen, so you did your PhD at EPFL. You finished a PhD in computer science, 2014. I think that was a very productive and very kind of, time where we all were working on multi-object tracking and a probabilistic occupancy map. And there was also, I can remember Zangs and Ram Nivatsia's paper about the NetFlow algorithm for multi-target tracking. I think you felt in this time and brought up very important contributions. And then Horesh started actually bringing this to actually commercial sector, started a company which was called Playful Vision. And what is really amazing is that he was able, and that was 2014, so close after his finishing his PhD, he was able actually to sell this company after a year to Second Spectrum. So congratulations, it must be really interesting, powerful technology actually you have developed during that time. And this company is actually a US company, LA based. And so you held Horesh held a senior director of computer vision products position there until 2018. And he's now vice president actually since then of the computer vision products part. So Second Spectrum is very successful actually in sports and sports analysis with computer vision technologies. Maybe last thing I would like to say about Horesh is that he's also a mentor and he's trying to give his knowledge, his advice to young people, to young entrepreneurs, at least in Switzerland, so since 2018. So there we can also learn, I think, quite a lot about Horesh and others about entrepreneurship and things like this. So I will stop here and yes, the floor is yours.
Thank you, Roman, for a great introduction. I hope that people would like the presentation. Try to do both. I guess that you see my screen, right?
Yes, I see.
Good. So I'm trying to do a small presentation. Of course, we don't have enough time. That would give you some flavor of what we're doing. And basically, like you see here, like a bunch of logos from EPFL, Playful Vision, Second Spectrum that you mentioned. And just like a small anecdote is that Second Spectrum, which was already a big company, has been sold to Genius Sport, which is a NASDAQ traded company in June. And now we are part of this huge company. But in any case, it's all started at the lab. And I just want to show where we're at right now. So, if you are watching football and you are watching the television and BT Sport, you would see that now we have this kind of like mini map, something, and the name of the players, and the ball is being tracked. So this is done in real time. And being visualized on television. And you could see that there is some kind of like a visualization over the goal and so on. So this is something that we are doing right now. This is like basically our technology. Yeah, and as I mentioned, it's all started. So yeah, well, we already did a small introduction, so I'm skipping it. It started all at the computer vision lab where we had only detection, you see that this is coarse, and we are doing, we have the positional data over in a dot. We had another project that was like tracking multiple objects from drones. So this is like the cafeteria of EPFL is located here, and you can see that we were using drones to track objects. And this is another like detection and tracking that we did with Honeywell, actually with the Prague lab, where I met Professor Jiri Matas as well. So it was like quite interesting. But definitely the most interesting part from my PhD was to track basketball players. This is a project that was funded by the Swiss government. And in here you can see that we are detecting the players from multiple angles and creating this type of a virtual view where we have the positional data and the numbers of the players. So this was actually presented, funny enough, exactly 10 years ago at ICCV 2011. And then what we had is basically a pipeline to get video cameras and to convert it into trajectories based on multi-commodity network flow. Basically network flow, this was that time. This was there was like no deep learning at that time. I just want to briefly show it just as a reference and to say what we're doing at the company. So in some sense, you can see here that we have the pre-processing. This means that we calibrate the cameras, we understand where the camera is located. We can do it in sport games based on the markers that we have on the field. At that time, we were doing it only in 2D on the grid, and we were like having a grid cell in every location on the court. And then, like as Roman mentioned, we had a probability of occupancy map. You can treat it as a detection, but this is the probability of a position to be detected. And at that time, we were doing basic detection based on background subtraction. Now we can use any other detector, but you can see that we have unidentified objects that are being detected over this grid. And the question was, okay, well, what can you do with these detections? We would like to track it over time, of course. So basically, we would like to have a different identity for each one of them. And as I mentioned, we use network flow. So I hope that some people are familiar with this thing, but basically we were having a graph that is basically taking all the detections that we had over time and combining the time frames. This was like forming the graph. We can represent the graph in 2D. We would and then the flow would be the movements from one timestamp to another timestamp. In that sense, the network flow was basically to have some kind of scrolls over the flow with some kind of flow constraints. This is the flow constraints were basically the continuity. You cannot, a flow or like an object cannot disappear in the middle. It needs to move from one time to another. We would like it to be smaller or equal to 1. So basically we don't allow more than one person to be in a grid cell. This is just like for simplicity, and everything needs to be positive. So when we are doing that, introducing source and sink, and this is basically how we solved it. Like basically we have a linear programming equation that we are solving, and this is providing us the tracking. This network flow was optimized at that time also to KSP. If someone is familiar with this abbreviation, this is like the K-shortest path algorithm. But still, you see that in here, like the tracking is very nice, but it is still unidentified. This means that we might have switches between players. We don't know whether we are looking at a player or a coach or a referee, and we would like to convert it into something that is more meaningful. So basically, we need to introduce identities. We need to introduce appearance, and this was basically my PhD, to introduce another term, not only the detection, but also appearance information. Appearance information is the probability that someone is belonging to a label, to some kind of a class that we think about. A class can be basically a team, right? Like in this case, we have 2 teams and the referee. And a class can be a jersey number, and then you have only 1 participant per class. and of course, like we can recognize the numbers. At that time, we were like doing template matching, but now, of course, like everything is deep, and we can recognize numbers. And the framework was taking, okay, well, how do you take this appearance information? You put it exactly on the grid on the same framework, and with the source and the sink, and track it over time. We used additional constraints. The flow constraints between the label, number of players at each label, and this is basically some like the equation that were there, and we optimized it even more and moved everything to tracklets. And moved it to 3D, and this is how we did the tracking. So basically, these are the results that we saw before. This was already presented at 2011, and you're saying, okay, well, looks nice. What can you do with it? You already understood that we could take it to the sport domain. We could use the same appearance information with face recognition. In here, you are seeing our lab, the computer vision lab, with every time that a face is being detected and identified, it's flickering in here, and we put all of this information on top of the data in order to have a consistent tracks. So, funny enough, in 2013, we also did it with masks. Like this seems quite relevant for these days. And already at that time, I could tell you that you can identify a person that is wearing a mask. In here, we had a small data set, which is only like few people that we had in the lab, but we had like we could still identify the people with the masks. We did it because we had a project to track medical staff in a hospital in Munich, and we wanted to know their identity as well. So this is just like the framework, the project that we had in the lab, and the Swiss government financed us, basically gave us the opportunity to create a small spin-off that was called Play for Vision. This was like the time of 2014. You can identify here the people that who knows Professor Pascal Foy, who was a co-founder in this company, and Charles and Pierre that are still working in the company. At that time, we were taking all the work that we did in the lab and basically demonstrated in the sports center of EPFL. You see that this is the volleyball team of EPFL. We showed it to multiple sport federation, and the volleyball federation took it. And interestingly enough, they signed a deal with us to take it to the World Championship, and we started this company in March 2014. In September, October 2014, we already been in the World Championship for men and women in Poland and Italy, and we did exactly what I presented before. We identified the numbers of the shirts of the players. We detected the players and the ball, and we created this kind of like a virtual view of every set that we had in volleyball, and we took it to other sport, to tennis as well. This is work that we did in the north of Lausanne. Basically, in here we detected the players as a whole and converted it into some kind of like stats, where what the heat maps are, like what type of skill they did, whether it was like a backhand or forehand or like a serve and so on. I'm jumping because the project, the company was working in bootstrap, meaning that it is doing projects, and we were living from one project to another, and another project came to our door, basically like asked us whether we can track horses in horse jumping competitions. We were not knowing anything about horses, but we took the project, and here is some of the results that we had in show jumping competition in Geneva. This was 2015, and we tracked the horses, and we even created this kind of like a virtual view with two horses that are competing against each other, of course, like that, competing in different times. But in order to explain how they were like why one rider like was much better than the other, we put them on top of each other. So this is another computer vision application that is utilizing our tracking and vision and video analysis.
Et regardez sur l'écran géant.
Okay.
La comparaison entre les.
The question was like, why to what is like the jump to second spectrum. Second spectrum came to us and saw all of this project and said, okay, well, why don't we do something big? Let's go and take over the NBA. They were like very strong in analytics. They took tracking data from another vendor and converting it into analytics into semantic understanding, and we agreed. We applied to second spectrum, which defined themselves as the next way to see in sport, and basically we provided this tracking component to second spectrum. And I'm just like showing some of results from 2016 after our integration. You can see here that we took it to the next level, to the NBA, and in here we're tracking basically. You can see here some of the NBA results, some football results, and so on. Just wanted to highlight about the NBA is that we are installed in all the courts of the NBA. We have about 10 cameras, and we're tracking all the 1,300 games that we have every season. Now it's the 5th season that Second Spectrum is tracking the NBA. I'm already going to the question of speed. And in here you can see that right now we have a real-time tracking system, which is basically below 1 second. From the action that is happening, we are already providing the tracking results. This is of course not working with the batches that we had, but it is an on-premise machine that is doing everything extremely efficiently. But just so to demonstrate it in this topic. Okay, so I'm jumping and like we are discussing about tracking, multi-object tracking, but the question is, okay, well, what is that you're doing with it? Because at the end of the day, it just look like a number in a huge grid that you're saying, okay, well, I would like to understand what is happening here. And the next level of after the tracking, we have an engine that was really trained with semantic understanding about what is going on. And you can see here that for every player, we have the shot probability, we have his location, and also what type of action they are doing. Basically, whether they are holding, whether they are doing a pick and roll, doing off-ball roll, and so on. Like this was trained with specialists that are like specialized in basketball. And then we could convert the XYZ position of all the players and the ball into meaningful understanding that is being serving the teams. Now, almost 100% of NBA teams are clients of us, and are taking this kind of like event information and can query all the videos that they have. Okay, so this is nice. We have tracking, we have semantic understanding. Can we do more? And the answer is, of course, yes. We can also augment the information augment the broadcast with our own data. So here you see the tracking information. If we know how the camera is located, where the camera is located, we could also take it and use it for like a promotional, for commercials, and also like to understand. So in here, like you see some of the cool visualization that we can do. We can use it for sponsorship. We can use it for highlights, and so on. Last thing that I would like to show for basketball is the work that we did with Marvel Cast. In here, we converted the NBA court into a theme of Marvel. So this means that every player was a hero, and every time that they were doing a shot, it was being visualized as the hero.
He is Captain America's pick tonight. You being Captain America, you know, and also being New Orleans native.
18 hero points now, 2 more than Draymond Green as Ingram buries a jumper. Draymond to the rim by the eye of Agamotto. Curry.
Good. And in here, so I just wanted to jump and to say that after the success in basketball, we said, okay, well, we need to move to the biggest sport in the world, which is basically football or soccer. If you are like sitting in the US, we signed a big deal with the Premier League after like a long walk of like convincing them and demoing and so on. Just as an anecdote, we said that if we are going to sign a deal with the Premier League, which was like very important for us. Everybody are going to jump to Lake Geneva in the freezing cold, and just like from the timing, you can see that everybody like jumped to the lake, and we had a lot of fun. And now we are the official tracking provider of the English Premier League as well. This is the 3rd year that we are doing it. And in here you can see like one of our cameras that is located. In here we're tracking the players, the ball. In here you can already see some new type of visualization. We are also doing a pose tracking. We're tracking it in 2D, and then we combine everything in 3D, with triangulating everything in 3D. So now we are also having, apart from the identification that I mentioned about the team understanding, the jersey numbers, we also have like team formation. We understand which player is in which location. We definitely have the pose, which is assisting us a lot. And with this, we can do many more things. So just like this is the tool that we were using. We can for example, visualize different tactics, or having dominant regions, like having different analytics on top of the broadcast feed that we have. We can have the minimap that we did and we showed before, right? Like, we just jump and say that in here, like if you haven't seen it before, so you can see also that the ball is being visualized, and people can understand better. Like even if they are not seeing the entire view, they can know where all the players are.
It's Christian Pulisic.
Yeah. And if you are asking, okay, well, so what is the as pose? This is something that we already seen before. So here is the same view from our pose tracking. So in here you can see that we are tracking the limbs, and we have like 20 key points. And here we are only visualizing it on a few of them. But in here, like once you have a virtual view of the world, like you can see it from the eyes of the goalkeeper, of the eye of the offensive player. You can do many more things. For example, we were doing with FIFA a trial to get an offside line automatically detected based on our lib tracking, such that because we have players detection, the ball detection, we can identify some key moments automatically, and then provide it to the federation, to the league, and to the broadcasters. And with this, I would like to, I know that it was like really, really brief. It was in a speed of light, but with this, I would like to thank everybody and to open the room for questions. I hope that you are still with me. Thank you.
Thank you very much, Horesh, for this wonderful presentation. So we have 5 minutes, so there are questions actually. So for example, there is a question, how many cameras are actually needed? So you mentioned actually, I can remember 10 cameras, for example. So how many cameras are needed for the EPL analysis?
So basically, the more camera angles that you're going to have, the better, because we are utilizing them for both like identify the players, reading the numbers, now understanding the team formation and so on, and also to triangulate the ball. And for this, you do need to have multiple angles. How many do you need? Like the more, the merrier. And I would say also the height is super important. So now the Premier League is a top league, and they can definitely afford 10 cameras to do that. They're using many more cameras for doing other work, like the low goal line technology or the VAR and things like that. In lower leagues, we are using less cameras. For example, we are working with the NCAA in basketball, and we are using 8, or we can use 6. It's only depend on how much they are like resilient to the accuracy. So this is 1, and 2. Basically, the longer batches that we're going to use, the better tracking that we're going to get. So if you are like, you're saying, okay, well, I'm willing to get to work with less cameras, but with 2 minutes of delay, okay, well, we can provide the product. But if you want to a real-time system, the more cameras are needed.
Thank you. There is another question regarding the 3D pose tracking. So there is a question, when you get such a detail by the 3D pose tracking, is it actually possible to measure things like energy consumption? So for example, that individual players, do you envision that this can be used for additional analytics, for example, also in the training or so?
Definitely, they're using it already right now to get key. So, for example, like the load that the player has, like the high speeds, like how many sprints do they run, and so on. Definitely, like the more granular we are going to be with our data, maybe like moving from pose into shape and so on, we would get even more insights. And yes, so the answer is yes.
Yeah.
And the only question is how sensitive we are to the accuracy. So if you, when working with the top leagues, you do need to be super accurate.
Mm-hmm. Thank you. There is another question. Actually, I also thought about this question because we are, as a community, we are caring about the single target tracking. And you mentioned that you're working on multi-target tracking, also with multiple cameras. Mm-hmm. So basically, are you also thinking to apply in a way single target short-term trackers as well in your kind of technology you're envisioning? Because I think you mostly use still detectors and do multi-target association in your technology at the moment, right?
So one note is that what I presented that was done from 2011 is already being changed dramatically in the company. I just cannot show what we have right now. So this is one thing. But with respect to the VOT challenge, in the VOT challenge, you are tracking objects that I haven't seen before. So in some sense, like you don't know what is that you are going to track. And in our case, hopefully we know everything that we would like to track. How can we combine them together is in case we have objects that we are not expecting in the scene and we would like to mask them. For example, if we have some either birds or some objects that are coming into our scene, and we would like not to track them or like to mask them out of the situation, we can use this type of trackers. This is one way that I see that this can be applied. And the second one is maybe as a union of different trackers. We have trackers that is tuned for people, but maybe we can use a generic visual object tracking that, and if they don't agree, we can alert a system that would improve in a specific place.
Mm-hmm. Mm-hmm. Maybe the last question. There is a last question regarding actually, I would say, brand new, let's say, for example, ICCV published papers, and then actually things you are using in your technology. So the question basically, as far as I understand, is to which extent you're replacing actually parts in your commercial system, in which speed or so, that when you read something new from ICCV, for example, that you adjust your test bed or your methods to improve your system. How does this work? This is a question coming to you.
So since our system is based on a multi-service or microservice architecture, we can replace many of the things. So definitely we are using things that I haven't not presented in here. So we are calibrating broadcast feed. We are using we are doing a segmentation of the feeds and so on. In that sense, I would say that the entire pipeline was changed. Like reading the Jersey numbers, for example, definitely each time that a new paper is being presented, we are trying it out on our data set, and if it is working better, of course, we are introducing it. We try to keep up to date. At the company, we are doing journal clubs. We present some of the papers that are being carefully selected from ICCV and other conferences, and we try to bring them into the commercial application that we have with the data that we have.
Mm-hmm. Well, thank you very much again. I think there is no other question. Time is also over. So thank you very much, Horish, again for this great talk. And I think we move further. So maybe you could give the screen to the next speaker. So the next speaker is C, I think. Like C.
Yeah.
So the next presentation is about learning spatial appearance memory networks for high performance visual tracking. I hope you can now take over the screen for you.
Yeah. Can you see my screen?
Yes, I cannot see your screen. Maybe you start the full mode.
Sorry. Can I begin? Or?
Yes, you can begin. Yes, but
Okay.
yeah, when you just start the presentation, and the floor is yours.
Hello, everyone. Good evening. My name is Xie Fei, and I come from Southeast University in China. So today I will briefly introduce my work, learning spatial appearance memory network for high performance visual tracking. So to begin with, we will show our contributions. Firstly, we adopt a segmentation-based tracking model, and we propose two memory banks, which all try to utilize the temporal information. And we also propose a dynamic memory module to relate the memory samples. And for our method, we only need less training source, and we can achieve high tracking performance. And this is our pipeline. We do memory banks are the main components in our pipeline. We present the appearance memory bank for adapting the segmentation branch to the temporal appearance variation. In particular, we stored the encoded key and values of continuous frame for the target appearance information. And we further treat online discriminative correlation filter as spatial memory network to model the mapping between the feature map and the target center. And the predictions from the spatial memory network are served as the position encoding for the appearance memory network result. And then the fused result are fed into the decoder to predict the target mask. And our appearance memory networks adopt non-local attention mechanism, which can capture the long-range spatial temporal information. And also it can be updated online, which is very suitable for the object tracking. And this is the mutual promotion from the dual memory banks. And the spatial memory banks can helps to filter out the noisy samples for the appearance memory bank. And also on the contrary, the appearance memory bank can offer the more accurate target center for the spatial memory network. And this is our dynamic memory machine to relate the memory samples in the appearance memory bank. This is implemented by deep Earth movers distance. And this is the visualization of our spatial temporal weights, and the transparent regions are more likely to be activated during the query operation. And our tracker achieves state-of-the-art results on 6 tracking benchmarks. And also we do the experiments on the video object segmentation benchmarks. We achieve very competitive results. And we also validate that our trackers, the superiority of our trackers to use the temporal information. And we also investigate the optimal memory size for the short-term object tracking. And we also do the aberration studies on the dynamic weighting module, and also and other factors such as the mutual promotion and the position encoding. And this is our spatial temporal weights from the dynamic memory module, and we can see our weights achieves a balance between the two strategies. One is use the linear decay strategy, and another is cosine similarities. And this is our visualization results of object segmentation. And this is the visualization of tracking. And our tracker can handle the challenging scenarios in tracking. And especially our trackers are good at handling the appearance variations because of we adopted the temporal information. And also our trackers are generalized well to the unseen objects. And for more details, please refer to our paper. Thanks. That's all, thanks. And any questions?
Thank you very much for the very quick presentation, I have to say.
Yeah.
So is there any question to the author? We have still time actually, so maybe I have a question. Maybe could you go back to the architectural picture of the method? I would like to better understand if you could maybe explain again how this memory is realized in this network architecture. Maybe you could just give some more detail on that.
Okay.
No, when you go further, maybe, yeah, on this pipeline picture, just to that we understand better. At least I haven't really understood how the memory is now really implemented in this architecture. If you could just elaborate on that.
The spatial memory. Spatial memory bank is DCF, the online filters. Yeah, it stores the feature maps and the heat map to indicate the target center. And for the appearance memory network, it stores the keys and the values, and the key and the values are encoded by the feature extractor with two separate convolution blocks.
So this appearance memory encoder and the spatial memory encoder, which is seen in this green row in this first part, this is a convolutional neural network.
Yeah. Convolutional.
Okay, and this is forming the memory, basically.
Yeah,
Is this correct, or because I'm just asking? Because then my next question is actually, how you can ensure that that this memory is in a way sustainable over a longer time. Because I'm not an expert in I have to say in memory-based networks, but I think there might be a problem also to lose information in the memory very quickly. So I mean, there is a whole bunch of work on this topic. So how can you ensure that what you have learned is not lost or overwritten or over time?
Yeah. Actually,
There is
yeah,
like in the LSTM, for example, this is the big problem.
yeah,
That,
I
you know,
agree
they
with
keep
you.
the information for a longer time, and there are a couple of tricks, and so just if you can.
Yeah, in this paper we just adopt some handcraft strategy. We just if also our experiments are all done in the short-term object benchmarks, checking benchmarks. So and also during the inference we will just slow away the earliest memory samples to make sure that the memory banks will not be too large. And this is another very interesting problems. There are many papers discuss this. It's like a memory management system, or you can have many other methods to deal with these problems. But in our paper, we do not discuss it in details. We just slow it away, and you can use some papers who are dedicated to solve these problems. And because we just do the experiments on the short-term object checking. So yeah.
Okay, thank you. I think there is no other question in the chat room. So thank you very much for this presentation.
Okay.
And I think it would be now nice if you could hand over to the next speaker, which is Matteo Danhofer.
Can I just finish two representation in a time? Yeah.
You have finished. Did you finish your presentation? Sorry, because I was thinking you finished.
Yeah, I have two presentations.
Yeah,
so
but your next presentation will come after the next speaker. So if you could please hand over to the next speaker, which is Matteo Danhofer.
Yeah.
And his presentation will be, the topic of his talk is first-person vision challenging for object tracking. Wonderful. Thank you very much. The floor is yours, Matteo. Are you here?
Okay, yeah.
We can see your video. Thank you very much. Yeah, sorry.
I've
the floor
lost
is yours. Thank you.
Okay. Just a second. Okay. So hello everybody. My name is Matteo and welcome to the presentation of our paper, which aims to answer the question, is first-person vision challenging for object tracking? This is a joint work between myself, Antonino Furnari, Giovanni Maria Farinella, and Cristian Micheloni. We work at the University of Udine and at the University of Catania in Italy. Let's start by seeing the motivation behind our work. In first-person vision, one of the most important tasks is to understand what the person that is wearing the camera is doing. This means understanding which action is performing and how the person is interacting with the objects of the surrounding environment. And knowing the motion of objects could be advantageous since it could provide cues about what's going on in the scene captured by the camera viewer. Considering the extended success of modern visual trackers on a large variety of domains, we wanted to use them for reconstructing the motion of objects. But after some preliminary qualitative experiments, we found trackers to work well in some situations, but to fail in many others. We hence decided to measure with numbers the extent of that performance. And to study the problem, we followed the standard practice of building a curated evaluation dataset, and hence introduced Track 150. This new benchmark is composed of 150 videos sampled from the Epic Kitchens dataset, which is currently the most diverse dataset for first-person vision tasks. The video sequences have been densely labeled with axis-aligned bounding boxes and have been selected by maximizing their diversity and by making sure that they represented well the usual situation happening in first-person vision. Overall, our dataset has comparable numbers to the most popular benchmarks in our community, but it offers complementary characteristics. For example, these are the persistent presence of partial occlusions, mainly due to the interaction between objects and hands, the fast motion of the scene due to its proximity with the camera point of view or the head motion, the significant light changes due to the shadows generated by the camera viewer, and the major aspect ratio variation to the manipulation of objects that can change their pose. We use standard execution protocols to perform an analysis, namely the one-pass evaluation, the multi-start evaluation, and the real-time evaluation. In addition to the widely used performance plots and measures, such as the success and the normalized precision, we introduced a generalized version of the robustness measure introduced by the VOT2020 challenge, which referred to as generalized success robustness. We think that such a measure to be particularly suited to evaluate trackers in relation to FPV tasks. We selected 31 trackers in our evaluation by making sure that they represented the most popular approaches to visual object tracking. And the distribution of the characteristics that is reported here reflect what is available today at the state of the art. In addition to those trackers, we developed two baseline FPV-specific trackers by integrating the ALTMU pipeline with the object detection model specifically developed for the FPV domain. Our one baselines use a simple, faster RCNN trained on Epic Kitchens to obtain candidate objects after a failure of the tracker, while the second one employs an object detection solution that reasons about the interaction happening between objects and the ends of the camera view. Here we show the performance of the study trackers achieved with the one-pass evaluation protocol. For reference, the shadowed results report the performance of the trackers on the OTB 100 benchmark. Overall, we can see that the combination of the condition present in first-person vision reduces the performance of all the trackers. And the generalized success robustness is the measure that suffers the major drop. The challenging scenario is also confirmed by the results achieved with the multi-start evaluation protocol. Considering the particular approaches, deep learning trackers emerge as the best ones, while those based on traditional methods are generally weaker. Among the first class of trackers, those leveraging online adaptations show a stronger performance than those based only on Siamese-based matching. And the proposed FPV-specific trackers show marginally better results, while we expect that improved performance will be achieved by carefully designed solutions that take into account the challenging aspects of first-person vision. We also group the performance by the attributes associated to the videos, and in the results that the most challenging factors are those that we discussed before. Other critical factors are out of use, full occlusions, and the low resolution of objects, as well as the presence of similar objects. We also labeled the sequences by the type of manipulation performed by the person on the target, if by one end or two ends. It results that tracking an object manipulated with two hands is more difficult, and this is because two hands posed on an object cause larger partial occlusions. Considering the performance with respect to the action performed by the camera viewer, we have that the action that change the state, shape, or aspect ratio of an object, for example, remove, squeeze, cut, or attach, generate other tracking scenarios. And also the sequences characterized by the wash verb lead trackers to poor performance, probably due to the extended amount of occlusion such an action generates. Finally, we conducted experiments to assess whether tracker bring improvements to FPV tasks that require object localization, such as the detection of end-object interaction happening in videos. Some of the trackers improved the performance of a pure detection-based solution represented in orange, and thence there is potential in the exploitation of tracking in first-person vision. The interesting point here is that we try to build a ranking of the trackers based on the performance achieved by the downstream application exploiting the trackers. And a different ordering with respect to the other rankings is showing up, suggesting that the tracking approaches contribute differently when they are deployed into applications. In conclusion, our work should be considered as a first step in studying the impact of the first-person viewpoint on object tracking. We are already going forward with extended analysis. From what we experienced so far, we can say that the first-person visual domain poses new challenges to the current state-of-the-art in visual tracking, and we expect better performance to be achieved by solutions explicitly considering the characteristics of this domain. Finally, the first-person community needs solutions that work best for their pipelines and that are not necessarily the first in the rankings of our community. For more insights about our study, please refer to our paper. We also have a web page which points to all the relevant resources. And we also provide Python code to download the dataset and to run the trackers. And that's all by my side. I'm happy to take questions. Thank you.
Thank you very much for this very interesting talk, Matteo. There is no question at the moment in the chat, so is there some question, please then ask it now. Maybe I have a question to you. So basically, we have seen before also that segmentation helps quite a lot instead of bounding boxes. So would you also expect in this application domain of first-person vision that this would maybe bring an approval to tracking?
So in the first-person vision community, there is not yet this necessity of segmentation. They are quite happy with bounding boxes. So they use bounding boxes in their pipelines, in the action recognition, action anticipation pipeline, and they are satisfied. We had the discussion about our direction about segmentation. And we also realized that it's difficult due to the particular challenges of first-person vision to provide consistent segmentation for some of the objects, especially when there is heavy motion blur to the head motion or to the camera motion. So in that case, it's not easy to provide an accurate segmentation for reference. And the bounding box is still working well. So for our further studies, we will try to use segmentation to have a better estimate for the performance of the tracker, but also for a better initialization. But for now, yeah, there is not this necessity in the first-person community.
So maybe I ask a second question because there is still no question. So so you have presented these results on OTP, and it seems there is really a drop in performance when you compare it to OTP. I mean, it seems so much more difficult, this task, right? So what are your ideas to improve the tracking in this specific domain now? What could be a potential idea, what you have in mind at the moment, or what your community has in mind?
So I think
like transformers, could this also help in your case to go to another network architecture, for example?
Yeah, we did some experiments that were not included in this version of the paper, but today will be included in another version in which we ran some transformer-based trackers, and we experienced better result. But we expect that better results will be achieved by trackers that will reason about the context and so about what is the person doing with the object, with the target object, in order to improve the tracking performance. So in this domain, you not always, but often you can rely on the position of the hands, on the motion of the hands in order to understand where an object is. So we expect such kind of cues to be included in the generation of first-person vision trackers.
So maybe that sounds, maybe Yishi is still here, I don't know, but kind of, you know, the web papers I can remember a couple of years ago from a dear friend of mine, Helmut Grabner, actually, about tracking the invisible, actually. So he had these supporters. And so when hands, for example, occluded actually a cup, for example, and this can happen very quickly, I think, in this kind of domain, I guess. Then they had, then he had his supporters in the context around this object to still track the cup, actually, things like this. So that would be something like an idea.
Exactly.
Which could be used. Okay. Usually you're here. Okay, now, so when there is no other question, then we should go to the third presentation, which is again 5C. So please, could you hand over again and share the screen for the last presentation of this session?
Hello, everyone.
Hello. So you have 10 minutes, Fai. Okay.
Okay. So
thank you.
I will.
The floor is yours. So I don't see at the moment your presentation.
Yeah.
Still.
Can you see my screen? Oh.
Not yet.
How? Is it okay?
I'm not seeing it at the moment. I don't know. Is somebody else seeing? I'm not seeing at the moment your screen.
Okay. Yeah. Can you see my screen?
It says that it has been started, but I don't see the presentation so far. So.
How about it? Is it okay?
No, not yet.
Yeah. But I will leave the conference and enter again.
So let's wait a little bit. Yeah, so now I see your presentation. Okay, thank you. So you can start now. Hello, can you hear me? I think you have to unmute. I cannot hear you.
Hi, can you hear me now?
Yeah, no, it's good. Okay, you can start now, please.
Okay, I will briefly introduce my work, learning tracking representations by dual branch Fourier transformer networks. And this is our contributions. We implement a semi-slack Fourier transformer-based tracker, and our model is only contrasted by attention block. And we also prove that our features are this instance discriminated, which is more suitable for object tracking. And also we achieve sold-out performance, and we're running at real time. And this is our pipeline, and similar to VIT, we divide template and search image into the regular tokens. Each token represents an image patch. And we use local attention model on the high resolution feature maps of the most shallow layers, and also the global attention model on the low resolution feature maps. And this can improve the inference speed. And finally, we use the cross attention blocks for the feature fusion. And this is our main components, the global and local attention block. Local attention block splits the feature tokens into the local windows and only computes the attention within each window, so it can avoid the quadratic computation flops. And the global attention block, it has the capability to model the long-range dependencies, but it will bring a heavy computation burden. So this is why we put the global attention block in the latter stage. And we do the experience for VOT benchmarks. We achieved the competitive results in some benchmarks. Our method doesn't outperform the CNN plus transformer-based trackers. This mainly because some internal factors of the network, which can be improved in the future. And we also do some comparisons to the some recent transformer-based trackers. Our tracker outperforms then in the VOT2021 benchmarks under the similar parameters and flops. And also we do the aberration studies to show that transformer-based feature extraction and feature fusion performs better than the traditional CNN-based semi-correlation trackers. And we also show that both the local and the global attention block are critical to the performance, and we had to make a trade-off between the model size and performance. And we will show some visualization results. For our attention-based features, the similarities between the target and the distractors are much lower, but the similarities inside the target is very high. It means that the attention-based feature is more focused on the inter-instance difference rather than the intra-instance. So it can make our feature more discriminative to the distractors. And also this is the visualization results of the cross attention block. And the attention-based feature fusion can gradually exchange the information between the template and the search branch, which is a kind of progressive refinement. And in the end, we will talk about our limitation and feature work. And we can see that our model is, the parameters is still very large. It's mainly due to the redundant independent module design. So we will further improve it by a more integral blocks. And we can see that the transformer-based model are not as fast as the CNN-based model under the same parameters and flops. It's mainly because the modern deep learning frameworks like PyTorch or TensorFlow does not accelerate the attention computation just as the convolution filters. So we hope it will be improved in the future. So that's all. For more details, please refer to our paper. Thank you.
Thank you very much for this very quick presentation. So we still have some time for questions. Is there somebody who's asking? So there is no question at the moment in the chat. So basically, so far as I've understood, I have to ask a question, of course. I would like to ask a question regarding this this problem, this computational problem you mentioned in the transformer. Could you just elaborate a little bit more on that? So basically, it's about the windowing process, I guess. So which is kind of exploding because you have to compute quite a lot of windows, the features, and just elaborate a little bit on that we better understand.
Okay, so the vision transformers are it's a problem really of the vision transformer because the attention computation is quadratic to the number of feature tokens. So the feature tokens is equal to H multiplied by W. So it's quadratic to your image size. So most of VIT works aims to reduce the computation burden. They may adopt many different methods to reduce the computation burden. One of them is to stabilize the image, the whole image into several local small images, and the attention computation only happens in the local windows. So it does not compute the global attentions. So it can reduce the computation burden. And so other vision transformer works also, they just use convolution filters to reduce the spatial size of the key and value features. And they didn't reduce the query features. So it is also another way to reduce the computation burden because the attention is equal to the query. The query multiplied the key to compute all the similarities. So you just need to reduce the number of keys, and the overall computation is reduced. And also you can reduce all the numbers of QK, query, and key. So that's why it's called the local attention block. That's all.
Thank you. I think that's very interesting because there was yesterday actually a presentation which from the MAR prize paper, and they presented a new transformer architecture called the Swin transformer, which brought a kind of breakthrough in this term. So I think it's quite interesting to follow these developments and to see how far we can go with the transformer also in tracking. That's very exciting. I think there is no other question. So when there is no question, then I think thank you very much again for the very interesting presentation.
Okay.
So that was actually our last paper in this session, our last presentation. Thank you very much for being here. I just would like to remind you that please stay tuned. We have now a break, 5 minutes, and then we will have the winner presentations, and I'm really looking forward for them, and I hope you also stay with us. Thank you very much.
Hello, everyone, and welcome to the third session of the VOT workshop. This session is dedicated to the winners of the 4 VOT challenges: short-term, real-time, long-term, and RGBD tracking. The first talk is about the RPT mask tracker, which won the short-term tracking challenge. The team behind this tracker are Jihong Fu, Liangqiang Wang, Qili Deng, Kang Du, Xingjie Liu, and Yunghong Wang. And the talk will be given by Jihong Fu. Please, could you start sharing the screen?
Okay. Hello, Alex. Can you hear me and see my screen?
Excellent. Please go ahead.
Okay. Let me begin. Hello everyone, I am Zhu Hongfu from Beihang University. This work was done under the cooperation between Beihang University and ByteDance. Our track's name is RPT mask. As the name implies, our tracker is built on the top of VOT2020 short-term window RPT. As Mete just said, our work is mainly focused on accuracy. So let's take a brief look at the pipeline of RPT. It consists of two stages. The first stage is a base check for object localization. It takes the first frame as a template, and the character frame and search region, and outputs the target bounding box in the character frame. The second stage is a general object segmentation network for object segmentation. It takes the target bounding box output by the basic checker at the center. Then collapse OII from the character frame as the inputs. And finally outputs the mask of the target in the ROI. Here are some bad cases of our baseline, which shows that our baseline has poor object detail segmentation ability and discrimination ability. The main reason is that our baseline does not make full use of the given target mask in the first frame. So we design an one-shot object segmentation network to make full use of the given target mask. In this network, we combine the features of the template and the ROI. Because our one-shot object segmentation network has a prior information of the target mask, it can make the target mask details more precise and distinguish the real target and the detractors better. Specifically, our one-shot object segmentation network is implied by an excellent video object segmentation method called STM-VOS. The network inputs the template with its mask and the ROI. After exchanging their features, we use two convolutional layers to map the feature map to a key feature map and a value feature map respectively. Then a close attention module is used to retrieve the features of the real target according to the features of the target template. So at the end of the network, we use a mask decoder to generate the target mask. In the mask decoder, skip connections are used to refine the details of final target mask. Besides, at the end of network, we also add an extra bounding box estimation network to assess the network training. On the right are the details of the close attention module. Here are some results of our model on the VOT2021 public dataset. We see that the target masks output by our model are significantly better than the ones output by our baseline in both target detail and discrimination. In terms of quantitative performance, our model outperforms our baseline by 3.4% of EAO. As shown in the figures, we calculate the similarities between every pixel of the template feature map and every pixel of the ROI feature map in the close attention module of the one-shot object segmentation network. Because there may be noise information similar to the target template around the target in the ROI. This noise information may be regarded as part of the real target by the network. So we use a top-K softmax function instead of a naive softmax function to normalize the similarity matrix. Here is the illustration, and below is an example. If we use a naive softmax function to normalize this vector, we will get a new vector with values 0.2666, 0.2205, and so on. We say that in this case, smaller similarity values will be relatively magnified. However, if we use a top-case softmax function to normalize this vector, these smaller similarity values are set to 0, which makes those larger similarity values still relatively larger. Here are some results of our model on the VOT2021 public dataset after improving the close attention module. Comparing to the similarity matrix with the naive softmax function, this one with okay softmax function has higher response values. The qualitative results also show that the problems we mentioned earlier has been well resolved. In terms of quantitative performance, this version of our model exceeds the previous version by 1.0% of EAO. So after being equipped with these two improvements, our model obtains an EAO of 0.568 on the VOT2021 public dataset. Here are some visualized snapshots in some challenging checking scenarios, where the pink masks are our models results, and the green masks are our baseline results. We can see that our models are significantly better than our baseline. Last but not least, it's necessary to take a minute to introduce the training dataset. We directly use the pre-trained weights provided by the VOT2020 short-term winner to initialize the base check RPT. It uses YouTube BB, COCO, ImageNet VRD, and ImageNet DET to train the network. Besides, for the training of the one-shot object segmentation network, we use YouTube VLS and Silency to supervise the mask head, and use GOT10K, LASOT, COCO, ImageNet VRD, and ImageNet DGT to supervise the bounding box head. And that's all. Thanks for your attention.
Thank you very much, Jihong. Like two questions here in the chat box. You in the last slide, you probably touched a little bit on that. Do you think the segmentation head would benefit from training on more segmentation data sets? And if so, what kind of sequences, content-wise, do you think would help most? Assuming that trivial sequences with well-visible targets would not improve training much. What would be your answer to that?
Yes. Obviously, more training data can improve the model performance.
But have you got like any ideas about like the type of sequences, what kind of examples would actually improve this? Like, how would you find like some difficult cases? Could you like use some of these contrastive learning algorithms to boost this?
Actually, we have analyzed each videos on the VOT2021 dataset. We found that if the video length is more, if the video length is more longer, then we will get more higher EAO.
There's a follow-up question. So how would the ground truth segmentation quality actually affect that? Do you require like very few accurately segmented sequences, or you could also like work, or maybe perhaps even better, with a huge number of approximately segmented one?
Actually, we found that the segmentation accuracy is more important than the robustness for the EAO improvement.
Another question is, for example, you've significantly improved the accuracy. And now the question is, what kind of change in your architecture do you think would also improve the robustness? Or do you think that the robustness is somehow already like at the top that can be with this type of approaches? Have you got like any directions that would be interesting to explore? And perhaps like your method is kind of like a two-stage approach. Do you see like how you could somehow like put all these things together in a more unified way, perhaps with better final outcomes?
Personally speaking, I think two-stage checkers will make the performance better. This is my personal opinion.
So do you think that keeping like two stages separately is actually a better idea than trying to somehow put all these things together?
Generally speaking, if we use a strong base checker and let me organize my language.
Yeah, sure, no problem. Just take your time.
If we want to use a checker with two stages, so generally speaking, we should do this first. We should choose a base checker with high robustness. Then we should choose a segmenter or segmentation network with high accuracy. And in that case, the total model will have high robustness and high accuracy.
Okay, thank you. There is like one question which is a little bit more technical, but perhaps you can also address it. Could you elaborate again on the improvement you made before the softmax? This is softmax slide, as it seems to be the key for the better accuracy.
Okay. Is this slide?
I think Roman asked that. Perhaps you can, Roman, you can unmute yourself and have a.
Yes, this is this slide. I think I just would like to better understand what because I think it seems to be this was the improvement basically, you know? So.
So
because before you do the multiplication, so you just in a way there's some kind of heuristics before you do the softmax, that the attention itself, which is this multiplication, is then a way. So these coefficients are in a way influenced by this what you have done here with the scatter and this top minus k. Maybe you can explain again because I haven't got it so far. So.
Okay. If we use the naive softmax function, when we calculate the similarities between the template key and the saturation key, we will calculate the similarities between each pixel of template key and each pixel of saturation key.
Or let me ask me the question different way. So basically, that's clear. This is the attention mechanism. So you have the key and you do the softmax, and then you make the multiplication with the value, and that's basically the attention. And you improved it because you show that on the left-hand side, you have the original, and then you improved it to the right-hand side, and you showed in the other slide the improvement in the segmentation. So my question just is that this improvement improved also the segmentation, right? Is this correct? Did I understand this correctly?
Yeah.
On the next slide, you show the images with the segmentation. So basically this improvement, what you have shown in this architectural picture, actually brought you to the better accuracy of the segmentation. Yeah, exactly what you show here. So these yellow rectangles, these are failures. And on the right-hand side, you did this, I don't know, some kind of heuristics you change a little bit the key before you do the softmax, and then the attention becomes in a way better, that the segmentation is clearer, and yeah, the accuracy is of course better. Is this correct? We don't maybe have to elaborate now why this is the case, but just to understand that this might be the key step, right?
In most cases, this condition is satisfied, or this condition is met.
I think, thank you. I think this is the reason. So I think for me, thank you. I think that's kind of the answer. So thank you very much.
Okay. Thank you very much. Are there any other questions? It seems that there are no further questions. So Jihong, thank you very much for your presentation. And
okay, thank you.
We'll move to the second talk, which is about the Trans-EM tracker, which won the real-time tracking challenge. The contributors are Xin Chen, Jiawen Zhu, Bin Yang, Dong Wong, Uchuan Lu, and Xiaoyun Yang. And I would like to ask Xin to start sharing his presentation.
Hello, can you see the screen?
Yeah, perfect.
Okay.
Start.
Hello, everyone. I'm Xin Chen from IAO Laboratory of Dalian University of Technology. I will present multi-template transformer tracking named Trans-TM. This is a joint work with Jiawen Zhu, Bin Yan, Dong Wang, Professor Uchuan Lu, and Xiaoyun Yang. Trans-TM is an extended version of our work Trans-T of CVPR this year. So I will briefly introduce Trans-T first. The motivation of Trans-T is to use attention instead of correlation to solve the bottleneck of the loss of semantic information and the lack of global information caused by correlation. So this is our Trans-T framework, consisting of 3 components: the backbone network, the feature fusion network, and the prediction head. The backbone network separately extracts the features of the template and the search region. Then The features are enhanced and fused by the proposed feature fusion network. Finally, the prediction head performs the binary classification and bounding box regression on the enhanced fusion vectors to generate the tracking results. We use a modified version of ResNet 50 as the backbone network. Specifically, we remove the last stage of ResNet 50. We also change the convolution thread of the downsampling unit of the fourth stage from 2 to 1 to obtain a larger feature resolution. The prediction head is 2 3-layer perceptrons. The feature fusion network in the red box consists of ECA based on self-attention and CFA based on cross-attention. 2 ECAs and 2 CFAs form a feature fusion layer as shown in this gray dotted box. The fusion layer repeats n times followed by an additional CFA to fuse the feature map of 2 branches, decoding a group of fusion vectors. We use n equals 4 by default. This is a detailed structure of ECA and CFA. Follow the design in transformer. They are both the residual structure based on attention. ECA is based on self-attention and CFA is based on cross-attention. CFA performs feature fusion. Compared with correlation, it returns rich semantic information. ECA and CFA establish dependence between long-distance features and aggregate global information. There are the attention maps of all attention modules in a representative tracking clip. We can see that from left to right, as the feature fusion layer goes deeper, attention strengthens key information, such as center and edge. Here is a video demo. The green box is ground truth, and the red box is a prediction of trans T. Benefiting from attention, trans T predicts accurate bounding box in challenging scenarios. Trans T achieves promising results on many tracking benchmarks with real-time speed, such as LaSalt TrackingNet, GOT 10K, and some small dataset. For more details about trans T, please refer to our paper, Transformer Tracking. Next, I will introduce the trans TN. Here is the structure of trans TN. We extend trans T with 3 modules: the segmentation branch, the multi-template design, and the IOU prediction head. The segmentation branch enables trans TM to predict bounding box and mask through an unified framework. The multi-template design records targets appearance change, thereby improves the robustness of tracking. The IOU prediction head outputs the IOU of the predicted bounding box, which is used to control the update of templates. Next, I will introduce the details of each part. For the segmentation branch, First, we respectively take out one vector from the template vectors and the fusion vectors. For the template vectors, we take the one located in the center of the space position. And for the fusion vectors, we take the one with the best classification score. Then we use these two vectors to calculate the attention map with the fusion vectors respectively. Reshape and concatenate the two attention maps and the fusion feature, and then fuse them with the low-level feature of the backbone network through FPN, and finally predict a mask through a three-layer perceptron. The multi-template design is very simple. We directly concatenate the feature vectors of two templates in spatial dimension and input them to the template branch of the feature fusion network. For these two templates, we keep the initial template unchanged and update the other. We use the IOU prediction head to control the update of the template. If the IOU is greater than the set threshold, the template is updated. For the IOU prediction head, we concatenate the bounding box prediction with the fusion vectors in channel dimension, and then use a three-layer perceptron to predict the IOU. Here are the results of the ablation study as shown in the first line. By submitting bounding box prediction, TransT only got 30 in EAO. As shown in the second line, by submitting the mask prediction after adding the segmentation branch, the accuracy of TransT seg is significantly improved, so it achieves 50.7 EAO. As shown in the last line, the multi-template design and the IOU prediction head improves the robustness of TransT, thereby increasing the EAO to 55. We tried to remove the attention module in the segmentation branch and found that the performance decreases as shown in the third line, indicating that the additional attention module is helpful for the segmentation. Therefore, in summary, in addition to TransT itself, the robustness improvement brought by multi-template and the accuracy improvement brought by the segmentation branch are the keys to achieving good performance. Also, compared with TransT, TransT-M is not only improved for VOT, it also has a stable improvement on other datasets such as LaSalt, TrackNet, and VOT10K. So my presentation ends here. Thank you very much.
Thank you very much. We have a question. I would kindly ask that those that have questions can unmute themselves and then just pose the question.
Yeah, thanks. I'd like to ask a question. First of all, thanks for this really nice presentation and the excellent tracker design. I was wondering about the architecture of TransT. Could you go back to the slide that describes it? You have a nice graph of the architecture.
This?
Yeah, this one. So I was wondering, you include CFA module immediately after ECA in two branches, and then you have a CFA that combines the two. So I'm sort of, when I was looking at the design of CFA, it looks to me like you're using you're rewriting one signal in terms of another signal, like you would rewrite the search region in terms of features of the template. It looks to me something like that. So I was wondering, why do you have to use two CFAs here? So my point is, what if you removed the two CFAs? Would the performance decrease? And if it would decrease, would it, like do you think in robustness or in accuracy?
Okay, so I think your question is, can I remove these two CFA, right?
Exactly. So what's their purpose, and what if you remove them?
Okay. In fact, CFA is the key component to fuse the feature from the two branch. In fact, we did evaluation study in our paper. We found that if we remove these two CFA, the accuracy and the robustness both decrease. I think just use one CFA is not enough to change the information of these two branch. Because I think in tracking, the interaction between template and the search region is very important. If we just, I think the cascade approach of CFA is better to fuse these two features.
So yeah, I was wondering, what is this fusion? I mean, how do you interpret it? What do you think it does? Obviously, it makes something simpler. Some steps after this are obviously, at least I think, made simpler. But I'm wondering why. Fusion is such a weird word. I mean, it doesn't say much. So what do you think it does?
Sorry, I didn't catch what your meaning. Could you explain?
Yeah, I'm wondering what the purpose of CFA is, like functional purpose. Fusion is a very broad word. I'm trying to understand what exactly, does it do?
In fact, the information of template or search region is not concise. We should strengthen some information and surprise some information. So if we only use ECA, it can only strengthen the information according to itself. For example, the template only strengthens the information according to the template itself. It can't get information from the search region in early stage. So So we use more CFA to make early to make these two features communicate early. And it can also help the future ECA to suggest the information.
Yeah, okay. So what you're saying is that, like, putting CFA in the upper branch will adapt the template features towards the features of the search region, and vice versa. Putting the CFA in the lower branch would adapt the features in the search region towards the features in the template. And if you do that in a cascade, you'll be better off in sort of adjusting both of the features such that in the end, when you're matching them, they would give you the most reliable results. Is sort of, that's what you're saying.
Yes, exactly. Yes.
Yes. Okay. Cool. Thanks. Thanks for this excellent presentation. Thanks.
Okay. Thank you. Are there any other questions? There is another question that CFA seems to be important in the compositional NX feature fusion layer. So maybe you can elaborate on that, Roman.
Yeah, Alicia. No, this was just maybe the conclusion of the previous discussion is that this CFA is important because you apply this n times, right? This feature fusion layer is an n times application of the ECA and CFA, right? And so it seems that in this compositional design, the CFA is important to in a way capture the information, right? So when we would leave the CFA out of the feature fusion layer, that would not be the case. And then the CFA as a last step, as a fusion actually, would be not enough. So this is my conclusion. This would be my conclusion.
Yes, exactly.
What do you think? Okay.
Yes,
Thank you.
Okay, thank you. Perhaps I can ask like a very general question. So this is like a time tracker, right? So with advances in hardware, things will get even more efficient. What would you like add here in this architecture to improve the performance if, for example, you can afford it in terms of real time?
Sorry, your question is how we make
for
it
example,
real time?
Yeah, so this is like a real-time architecture, right? So
yes,
that hardware will become like faster. Would you then, for example, take a bigger backbone, or what would you add to improve the performance in terms of like robustness and precision if you could actually add things and you would have like a faster hardware, for example?
Yes. So your question is, we can add some modules to make it more accurate or more robustness. Yes. In fact, we also want to add some modules such as the some MOT method to help the tracker to help the tracker from the distractor. So in fact, if we just make the architecture bigger, for example, we use ResNet 101 and or we use more feature fusion layers, we found the performance decrease, in fact. So I think the bigger architecture is not always work. maybe some module with more function. It can help the network to. It can help the method to obtain better results.
Okay, thank you very much. Yeah, that was my question. I guess in the interest, Shin, thank you very much for your very nice presentation, and we can move on to the third talk, which is about the MLPLT tracker, which won the long-term tracking challenge. And the team behind this tracker are Matteo Dunhofer, Christian Simonato, and Christian Micheloni. And I would like to ask Matteo to start sharing the presentation. Perfect, thank you.
Yeah, can you see it?
The way, okay. Yeah, it's perfect.
Okay, thank you. Hello, it's Matteo again, and this time, welcome to the presentation of our solution to the long-term tracking challenge, which is titled Fusing Complementary Trackers for Long-Term Visual Tracking. This has been a joint work between myself, Christian Simonato, and Christian Micheloni, and we are all based at the University of Udine in Italy. Our motivation lies in the realization that current trackers such as Stark and SuperDIM, which have been previously considered to be short-term, have now reached performance comparable to long-term trackers. We analyzed in depth the performance of such trackers and found complementary characteristics. Generally, Stark provides much more accurate bounding boxes, which lead to a higher overlap on average. However, such an overlap is often inconsistent with the confidence of target presence predicted by the tracker. On the other hand, SuperDIMP predicts less precise bounding boxes, but whose overlap is definitely more consistent with its confidence predictions. Given that such well-performing trackers are not too computationally expensive, it is feasible to apply fusion strategies on top of them. Many works in the past proposed methodology to fuse the complementary characteristic of trackers, but they focus mainly on the short-term tracking scenarios. We hence decided to explore such a direction of tracker fusion in the context of long-term tracking. Particularly, we wanted to understand to which extent we could push the performance just by combining two complementary trackers, without the need of the systematic approach composed of tracker, redetector, verifier that has been exploited for long-term tracking in the last years. So we executed the two trackers and achieved the following numbers, which form our bottom line results. We first tried some standard fusion baselines. For example, we averaged the bounding boxes and the confidence values produced by the trackers. If the blue and the red are the prediction of the two trackers, we obtain this bounding box and this confidence. We also tried to select the best bounding box according to the tracker's confidence, like this. And we even tried a more sophisticated approach we published last year. In this case, the performance of the trackers is evaluated by an offline learned deep network trained via reinforcement learning to predict the expected future performance of each tracker. Then, based on such an evaluation, a decision strategy that selects the best tracker is implemented. The first two baselines fuse the performance of the underlying trackers, but achieve marginally better results. The latter instead does not work well, and this is because it's supposed to work for short-term settings. We hence came up with the idea of developing a simple decision strategy based on an effective tracker evaluation function. Considering the extended usage of target verifying module based on MDNet, we decided to exploit such an architecture in our evaluation strategy. And let's see how we use it in our tracker MLPLT. At the first frame of a video, the underlying trackers are initialized according to their methods. The verifier, which is initially pre-trained offline, is adapted to the target of interest by extracting positive and negative patches around the grounded location. Then, at every other frame, our solution first executes the two trackers. The patches extracted from the predicted boxes are given to the verifier, which outputs the probability of target presence in each patch. We initially considered a decision strategy based on the maximum value predicted by the verifier to select which of the two boxes to use as target localization. This strategy worked, but the proven was again marginal. Considering that the underlying trackers have some ability in predicting the confidences, we combine them to those of the verifier in order to have a better estimation of the overall confidence. And we thresholded such values to obtain Boolean variables expressing whether the two trackers are following the target or not. And we also find combining the binary values of the last 5 frames to lead to a better estimate of target presence. And these ultimate numbers can be used to select the best tracker. It can happen that 2 Booleans are equal. In that case, the output of Stark is preferred since it is more spatially equated. And this combination in the evaluation procedure improved a bit the performance. But until now, our solution just evaluates and selects the best bounding box without interaction between the two trackers. Once the output bounding box has been selected, we propose to correct the performance of the failing tracker. This is achieved by replacing its last known target position with the one considered correct. In the next frame, this allows the corrected tracker to compute a searching area which is better aligned with the true target, ultimately correcting it from errors and drifts. And this procedure brings a major contribution to the performance of our tracker, making us gain almost a 4% in F-score with respect to the best of the underlying trackers. After this whole process, and when the evaluation strategy is in accordance with the meta updater, the verifier is updated in the usual way. We found this solution to generalize well also to other benchmarks such as LASOT. But at this point, we will have finished in second place at this year's VOT challenge. To initially enhance the performance of our tracker, we introduced 2 improvements that enable a better discriminative performance of the verifier. Particularly, we introduced these 2 improvements to the Stark tracker. The first one was to use an adaptive searching area. In a new frame, Stark's original searching area would be like the one represented by the dashed rectangle that includes matching relevant information. So for all those situations in which our evaluation strategy is sure about the target to be present, we halve the searching area factor, ultimately obtaining a searching area like this one. And we found this strategy to improve the tracking performance of Stark. When the target is considered to not be present, we set the searching area factor back to its original value. And this helps in the redetection of the target. The second improvement aims to correct this kind of behavior, which we found to be due to the change of the dynamic template strategy used by Stark. In such cases, the confidence given by Stark could be still higher. But given that such bounding box is not consistent with the motion of the target, we discard it by considered as a prediction having confidence equal to 0. And such correction have an important impact on our methodology because they remove polluted sample from the training set used by the verifier to learn online. Without such wrong a sample, the learning is more consistent and the resulting evaluation performance is improved. And this leads to an increased tracking performance overall. And basically that's it. Thank you for your attention.
Thank you very much for the interesting presentation. I think we have one question in the chat. Matei, would you like to ask directly?
Yeah, sure. Why not? So thanks, Matteo, for a very nice presentation. I was wondering in the tracker interaction step, where you showed that you moved the tracker to the better tracker position.
Yeah.
Here, yeah. So I'm wondering, do you just move the tracker or do you also reinitialize it at that position?
We found just to move its last known position to work back without reinitialization.
You tried reinitialization.
Yeah, we tried to reinitialize it, but since the corrected bounding box is not as correct as the ground truth, we found to make the tracker build a new target model that would use incorrect information. So we found to use the model starting from the initial frame to work better.
Okay, interesting. Thanks. That was the question. Thanks.
Thank you, Hyunjin.
Hi, thank you for the presentation. It's very nice work.
Thank you.
I have one question about the scale. How did you handle the scale changes, especially the drastic scale changes?
The final, so in this case, we simply calculate a ratio between the last known target position and the position given by Stark. And if it's outside some ranges defined by some threshold, we discard such a prediction and consider it to have a confidence equal to 0. So basically, we are saying that the prediction of Stark is not consistent with the target motion, and hence we try to not use it in the tracker evaluation.
Okay. And how about the partial occlusion? So there's some increasing, like when the object is being included, then the object looks getting smaller, like?
Yeah, that's mainly due to the Stark ability in addressing partial occlusions, and we found our verifier to be very consistent with such kind of bounding boxes. So it gives higher confidence, and it's in agreement with Stark, and that's why it is selected in that situation.
Okay, thank you.
Thank you, Roman.
Yeah, I would like just thank you very much for this very nice presentation. Just maybe a comment and a little question. So basically, you actually came up with some kind of meta learning where you have multiple trackers, which you kind of meta learn. And that reminds me very much to actually stack generalization. So basically, something which came up in the 90s by David Wolpert, and that's a nice way how you can generalize, right? So I have expected this better results, and maybe the little question is, would it be possible, do you think, that you choose in a way the trackers where you could in a way share, let's say, the backbones, or so that you could improve the efficiency of the overall tracking method? And would this be something you could imagine or so?
Yeah, I think that an evolution of this solution could be a strategy that kind of fuses the complementary characteristics of the two trackers in the feature space. So some kind of backbone or some kind of matching operation or fusion operation that tries to take the best out of the two trackers and to merge them maybe during the learning phase also. So
yeah, but during now you compute. How do you do that now in the implementation? I mean, you have these different trackers, let's say the Stark and other, and you compute all the features. You just compute every network. You do inference with every single tracker, right? And that takes a lot of time, I would say. Could you,
of course,
think about sharing, sharing, bringing that, at least the feature backbone together where it's possible, right? That you just improve the efficiency, things like this.
Definitely. We didn't spend much time on optimize the code, the processing, and so on. But the two trackers are one independent from the other, so you can actually execute them in parallel, and you save it almost half of the time. So again, if you then consider that they share backbones and the operation, then the speed can be ulteriorly improved.
Thank you very much.
Thank you.
Thank you. Thank you, Matteo. I think in the interest of time, we have to move to the last talk. Last but not least, in this session is about the Stark RGBD tracker, which won the RGBD tracking challenge. The team that contributed to this tracker are Xinyu Zhang, Bin Yan, Lijun Wang, Owen Pang, Dong Wang, Huchuan Lu, and Xiao Yunyang. And I would like to ask Xinyu to start sharing the presentation.
Hello, could you listen clearly?
Yeah, perfect.
And the screen share?
Yes, can you please just put it in the presentation mode? Otherwise, it's perfect.
All right.
No, it doesn't look like this. Looks more like for the presenter in the presenter mode.
Maybe like this?
Yes, perfect. Thank
you. Well, thank you. I'm honored to give the talk about our method for the VOT RGBD competition. This is the outline of my presentation. And at first, I want to talk about the powerful RGB tracking baseline we use. Yeah. So to fully exploit the RGB modality, we need a powerful RGB-based tracker as the baseline. So we adopt the powerful transformer-based tracker Stark in our method, just like the last, as in the last talk. And we replace the original ResNet 50 backbone with DEIT to further strengthen it. And we also adopt the Alpha Refine, which is a refinement module that can boost the quality of box estimation within a small search region. The small search region like this is generated by extending the prediction of the base tracker. So we can modify any tracker's search region into a smaller one and adapt it to a Alpha Refine module. So we just adopt a smaller search region. We just take a Stark with a smaller search region as our refinement module. Then we combine the Stark and the Alpha Refine modified it by the Stark, and we get the tracking system like this. The original Stark achieved an F-score of 68.1. And after, by changing the backbone, we improve the performance to 71.8. And by using the Alpha Refine modified it by Stark, we achieved a performance of 73.4. Although the baseline tracker has already achieved very high performance, we still notice that some failure cases in the simple scenarios. As shown in the figure, the Stark prediction is off the target, as shown in the as indicated by the red box. We observe that it is because the target appearance changes and the Stark get confused. However, at the same time, we run a DIMP super tracker and we found it performed well, as indicated by the green box. So this observation indicates that the tracker with online updating strategy are complementary to Stark. We believe ensembling them is very possible to boost the performance. So we design a pipeline for unifying the two trackers. We mainly introduce the key components here. At first, the Stark and the DMP Super perform tracking independently so that we can get two results in the same frame. And how do we select the final output? We by default take the output of Stark as the final output. In this situation, the DMP will update its center following the output of the Stark. But when the confidence of Stark is low, such as lower than 0.2, in this situation, we also require the DMP Super's confidence score higher than Stark. Then we will output the DMP's confidence and bounding box as our final output. It was noting that the Stark may be too confident as some distractors, so that we design a motion model to rescore the Stark confidence in order to suppress the sudden position change of Stark prediction. We also observe that DMP may stick to some wrong object, preventing the Stark from refinding the correct target. So when DMP is on duty, we decay the confidence of DIMP gradually to create more chance to switch back to Stark. This producing the final tracking system of our method. The output will be refined by the alpha refine module, as mentioned before. At this stage, our method achieved a performance of 75.6 F-score. For now, we only use the RGB modality. And about the depth modality, we have some attemptation, but we didn't get performance improvement. But we still believe that depth modality is of great value, because with the depth modality, in theory, it is possible to model the 3D appearance and the 3D trajectory of the target, and the depth of the same object should be similar, and can help us to discriminate the target from the background. And the depth modality also has the potential of modeling the 3D environment. We found the difficulties we encounter in using the depth modality is as following. We found many depth maps in the dataset only contain few discretized depth values, as shown in the top row. This just squeezing the points of different depths into the same plane. and we think the depth value is not accurate enough. For these depth maps with good quality, as shown in the bottom row, the RGB modality is good enough with our RGB tracker. With our RGB tracking system, it has done the job very well. So the depth information provides limited help. We show a demo to further explain the problem. The depth value of the same object, the depth value of the different part of the same object differs too much. This should not be the real shape of the object. We also observe that the depth value changes discontinuously. This may be another problem caused by the different part problem. This makes it difficult to model the 3D trajectory of the object. And we find the misalignment between the depth modality and the RGB modality. If we want to precisely localize the object in the depth modality, the misalignment prevent us from doing this. And yes, so the depth modality, we find it's very as a result, our temptation of taking advantage of depth modality failed to work. For example, we tried to take the depth into the motion model to modeling the 3D trajectory, but the trajectory deteriorates because of the inaccurate depth value. We find here we show two 3D visualization of the RGBD data. The right one is from the tracking data set, and the left one is of very high quality. If we can get data like the left figure, we can get information. We can get more information about the target, including the 3D shape, the 3D environment, etc. So that we believe that the depth modality of high quality has greater potential in object tracking. We draw the conclusion as following. For existing data, RGB modality is more informative than depth modality, especially with the powerful RGB baseline tracker. So we need depth data of higher quality. We also observe that the tracker with and without online updating, with and without online updating are complementary. Assembling different types of tracker will boost the performance. How to assemble them efficiently remains to be explored. As mentioned in the last talk, we don't share the feature or something like that. So the speed is a problem. That's all. Thanks for listening.
This has been excellent, especially all the comments related to depth, because this is indeed the tracking challenge which in which one should combine and take the advantage of both RGB and the depth. And Song has been working in this area for quite some time, and he would like to make some comments.
Yes, and thank you for your presentation.
And it's true, there's some problem about the depth, no matter the CDDB or depth track. And we found most issues happened when the outside scenarios or some long distance scenarios.
Song, can you please like move closer to the microphone and please can you repeat?
Okay, thank you. Sorry.
So how about now?
Yeah, now it's much better.
Okay, sorry for that. And it is true, there's a lot of the issues for the depth and RGB element. And most issues happen in the outside scenarios or the long distance scenarios. And we think it may be because the camera, when we try to catch the depth values and the object or the target, they move far away from the camera. So the depth value missing a lot. And it is also true when we have the good depth values for the indoor scenarios, the RGB also perform very well. And this is also why we add some more sequence for our depth track. We try to find some scenarios when the RGB tracker cannot perform that good. And you must need some depth cues for the tracking of some things. And unfortunately, we think in the CDTB, there's no kind of the sequence. You must need the depth cues. We also run some SODA RGB trackers on the CDTB sequence, and we found only the RGB also perform very well, no matter you use or don't use the depth tracking. So we start to think about when some specific scenarios like the pure dark, the dark side, or when the object has the same color as the background. For example, when you have the white color box and the background is also the white color wall. So in this case, maybe depth is useful for the RGBD trackings.
Great. That brings another problem. I think if the thing is dark, is there any problem for the RGBD camera to get the precise depth value?
Yes, we have several sequences in our depth track when we do record some video in the dark room, and in the RGB it's hard to see the target even for the humans, but the depth cue is still perform normally, and you can do some tracking on the depth channel. And for the 3D reconstruction, because the Uyghur's paper for the OTR, they reconstruct the object from the depth image. And most of this kind of the reconstructions they perform on the box, because there's a lot of the target, they are the boxes in the CDTB sequence. So I think it may be a little bit easier when they do the reconstruction on the this kind of the target is very regular and very easy to perform the reconstruction. Yes, and when we try to record some video for the animals, and we found it's so difficult to do the reconstruction on the animal target. For example, the cat or the bird, they change so much, and we also have some issues when the target moves so fast, and the depth and RGB they are misaligned. It happens very often.
Thanks, Song. Matej has another question.
Yeah, thanks. Thank you very much for the presentation. I find it interesting that you use a motion model. I find it interesting because motion models used to be quite popular at some point in tracking, and then they nearly disappeared from tracking. But in your case, you're able to show that using motion model actually helps you quite a lot. And I was wondering, what kind of motion model did you use?
We simply calculate the velocity of the box and monitor it. If it changes suddenly, we will suppress its confidence, such as in a Gaussian model.
So it's kind of a nearly constant velocity dynamic model. So you're placing a Gaussian on the predicted center of the target. Is that right?
The Gaussian is the velocity, the value of the velocity. If the velocity is far away from its previously prediction, it will take a very small Gaussian value. Am I clear?
No, I don't know. So is it like, are you using like a formal motion model, like a Kalman filter with a defined nearly constant velocity or nearly constant acceleration model, or is it something else?
Adjust the velocity.
Okay, so you use sequential positions estimated by the tracker, and then from that you compute the velocity between pairs of frames. Is that right?
Yes.
And then what do you do with this?
If the velocity change suddenly, oh, well, I know. Yes, the acceleration. If the acceleration is very, yes, very large, that just
so
leads
it's nearly
to
constant acceleration model, sort of like you place some sort of inertia in there in the motion of the target, I suppose, in this way.
Yeah, something like that.
Okay, cool. Thank you.
Thank you.
Thank you too.
I have a question. I have actually two questions to you. So basically, I've never worked with RGBD so far, but because you said that that you need a very good depth data actually. So basically, the property or the way the depth data seems to be quite different from the RGB data, in the sense that there are irregularities and there is no kind of a lot. It seems that there are some kinds of assumptions missing with this kind of data, because as far as I've understood, you treat in the inference process or in the neural network to treat the depth data in the same way as the RGB data, right? So it might be that one has to, I don't know, treat that differently, right? Because like CNN is assuming a smooth image, for example, right? Because you apply these filters, right? So basically the depth data doesn't hold these kind of assumptions, implicit assumptions. So maybe one would have to improve or do things differently for this kind of data. And the second comment is basically because I think also Jone said, it's not clear, how the depth might help. So maybe just a comment from my side. So is it like with the affine camera assumption, for example, that when usually in this data, what I've seen so far is that the distance between the camera and the object is quite large compared to, let's say, when you just imagine the surface in 3D of the object itself, they're usually planar. So this distance, in the surface itself is much smaller than the distance between the camera and the object. And when you would come closer with these two distances, so just imagine you would have really a very rough surface in 3D and a smaller distance to the camera, then maybe the depth would start helping you very much in the tracking. I mean, that's just, I don't know what you think about these two questions.
For the first question, I guess you mean we have to treat the RGB modality and the depth modality separately. I think if you treat the, for example, if you treat the depth as some sort of attention, or as it is also a Euclidean data format, unify the well, processing them in similar way is okay, I think. They don't have to
so basically what I mean is that the depth data as well as the RGB data finds its way in the convolutional null network. That's right, or have I maybe missed something? So both data is processed by convolutions, basically, or in a convolutional way, you know. And these convolutions, they have certain assumptions, for example, that you have local smoothness and this kind, and this is not given in the depth as long as you have not really nice, perfect, nice depth images, as you have shown actually in one of these images. So maybe there could be, you know, by thinking or rethinking this, you know, getting an improvement on that. This is just a comment. So, and just the thinking, you know, that maybe one has to treat that differently, and just to consider this problem of that you miss depth information basically, and it's normal that you like these discontinuities are always happening in real world, I guess, you know? And that's actually what you also have seen. So I'm stopping here. Okay, I'm sorry. But my second question regarding depth in general, you know, that depth helps, of course, when the surface starts getting, you know, very like the surface itself, like a body is quite planar when it's seen from the distance, right? So well, that might not help you, but when you see, let's say, a person very close, and you know, you have a quite, you know, kind of some kind of surface distances, you know, like some kind of three-dimensional changes on the surface, which are very specific for a specific object, then of course that there is some information which can identify the object, right? And then that might help quite a lot, I guess.
Okay, so I think we have to stop here. Thank you very much. Thank you very much for the interesting discussion. But then, in the interest of time, I think Shinyu, thank you, and I think this concludes the session. A big thanks to all the presenters for the interesting talks and the discussion, and the audience for participation. So thank you very much, and I'll hand over to Jerzy. Thanks.
Thank you.
Okay, Alex, thank you. We should conclude the whole VOT session with the feedback sessions and then perhaps some final remarks. I'll share my screen and ask the feedback session participants to unmute their microphones. So hold on a second. So the session participants are all the four winners and the keynote speaker, Horesh. So Matteo, Shinju, Shin, and Jihong, please, it would be nice if you unmute yourself. Thank you, Horesh. Thank you, Matteo. And
Hello.
Jihong. Okay, good. So we are all here, and we as the VOT committee, we are always interested in feedback on what we do, and we prepared some sort of questions which are possible to answer, but anything from the audience would be even useful, or anything that you have actually thought of. And just I will read some of those things. Maybe don't feel obliged to answer to anything, and maybe your questions would be more interesting. So that we will have a 10-year anniversary. We could do some sort of retrospective challenge next year. Maybe a question about data sets. You can ask, we can discuss things related to the evaluation that we see. We think that the anchor-based system is quite effective and working well at VOT, but other challenges, they start still with the first frame, which makes the whole evaluation first frame dependent. Or actually it says, but because usually the first frame is a very special frame. The first frame will not be somehow occluded or non-canonical view and so on. So another question could be about, we can talk about ground truth quality. We can talk about problems with the VOT toolkit. Maybe what makes VOT less or more attractive to the community. And maybe the final question is the most interesting one. What type of challenge should we introduce to motivate some interesting research directions? So this is what we thought of as the VOT committee, but the main thing here should be input from the people who are not the VOT committee. And I think that the number of participants is now fairly small. So I think that if you just ask your question or express your opinion, it'll be fine. So please go ahead, and any feedback is interesting and welcome. I'm looking at Mate and Horesh, and they look like some people that even if I promise 2 beers, they wouldn't talk.
I can start.
Okay, go ahead, please.
So, considering the history that now the VOT challenge and the knowledge that they acquired about the methodology, about the evaluation procedure of tracking, it would be interesting, in my opinion, to evaluate the impact of visual tracking on other computer vision problems or in other computer vision domains. This is because now we are working with first-person vision people, and there they want to understand which is the contribution of a visual tracking algorithm. So it will be interesting to understand if our procedure of optimizing our performance measure then translates in better performance in other domains. So in domains where the output of the tracker is used by other algorithms in other pipelines to achieve an higher level output and higher level behavior. So it could be.
Okay, thanks. I got it. I wrote it down as something like check the correlation of, let's say, VOT metrics with some downstream metrics. We have thought about this for things like maybe, well, we think that, for instance, segmentation directly links to some sort of video editing. If you want to remove something from a video sequence, if you segment carefully, you are fine. But you are stressing this like first person vision. So okay, if they have their like maybe activity recognizers and things like that, object detectors, and if improvement in our, okay, so if replacement of a tracker by a tracker performing well in VOT is good, it will, okay, these correlations will be useful and we should look at that. Okay, thanks. So, and okay, so good point, I wrote it down. Any other point, Matteo? Anything triggered by the questions or?
So, yeah, maybe some point that was also discussed last year in the panel, if I remember correctly, was the point of trying to include other benchmarks in the VOT toolkit. So that, in my opinion, would be a good strategy to also make the evaluation even more consistent across data sets in order to assess with the same protocols, with the same performance measures. So with the anchor-based procedure, the consistency of trackers across different domains.
So do I understand it that we would take a benchmark like LASSOT, say, take their data, maybe ground truth, and run our evaluation methodology on that data and ground truth?
Yeah, exactly.
Okay, okay. Point taken. Okay, thanks. So Horesh has cleared his throat.
Yeah, so I think that's like it is very interesting. Like I think that I'm definitely in agreement with Matteo on how like one CV task is being contributing to the entire system, because at the end of the day we're building applications and systems, and we need to see how one block is assisting. So this is one that I definitely like agree with. The other side is that in some sense, like all the data sets that I've seen is you have the moving object and you also have the moving camera. And I don't know how much you are like considering the camera motion, because to some extent we can stabilize it, we can calibrate it, we can do something on that front. And there is a clear challenge like to deal with it if you are only looking at the tracker of the object without considering the camera movement. I don't know like how much you
I take the point, and I was thinking about that. So for instance, if we had a footage from a drone which would be rotating or maybe jumping around in the wind, then the apparent motion of the object would be also very jumpy, and no motion model would work unless we first compensate for the observer motion, for which you can use the whole scene rather than the object itself. Okay, so I would say introduce in the database, like if we introduce a sequence which requires it, people will do it. Because they want to win, and they realize, aha, to do this, if I have a small object with a jumpy camera due to the, I don't know, like the drone chasing the airplane or something like that, then the camera motion compensation has to come in the equation. Yeah, okay, good point. So we always look for sort of diverse data set, and to have a significant, maybe random camera motion. It also affects things like blur. So if you have a jump due to the camera motion, you will have a sort of predictable change on the appearance of the objects. So these things are correlated. So, okay, good, fine. Okay. So, maybe I can't see on the list the other panel members, the winners of the challenges. So guys, would you like to comment? Maybe they have left. I'm not sure, because they were on the list of participants. Let me have a look. Yeah. Okay, we have no. Yeah. The winners have not joined us. The others, besides Matteo. So maybe any comments from the audience, from the VOT committee. We have like 3 suggestions, which actually is a good result. Heavy moving camera, integration of data and the ground truth from other benchmarks into the VOT protocol evaluation system and so on, and check whether our metrics are highly correlated with metrics and performance in downstream domains and applications. Yeah. Which sometimes it's not so easy to get the information what exactly is the downstream important metric. Okay, so
I don't know if another interesting suggestion could be maybe do some rankings using different kind of state representation for the target. Like for example, okay, the segmentation we know is the best one, which give us the shape of the target, but maybe in some application the bounding box is enough, and in other application even the barycenter of the target could be enough. So understanding if there are particular tracking principle or approaches that are particularly suited for the state representation could be interesting to study.
Okay. So Horesh is like a person who is applying the results of tracking, and Matteo on the panel is the only user of the VOT machinery. So perhaps it would be good if some other people from the audience express some opinion about whatever we should change, whatever we should do in the VOT challenge. So for instance, from what you were showing, like for Horesh in the keynote, it's mainly multi-camera tracking, and it's as you said, it's the main difference is that you are doing specific object tracking. So it's actually a close integration between detector of a specific class and a tracker. Maybe so it's from this model-free tracking, it's quite far. And as you said, the only thing that came to your mind would be to show whether a generic tracker could in some situation, well, you said two things, like unexpected objects on the ground, or maybe some whether a generic tracker could sometimes benefit the super specific tracker, and or maybe to show the other way around, saying if you have a superb person or football player, basketball player tracker, don't expect anything from a generic tracker, because the specific information is stronger than anything that can come from a better method for generic object tracking.
Yeah, so to some extent, I do think that for a commercial application, you would like to overfit to the problem that you are solving. So in some sense, like a basketball player is not a regular person. So it's not a regular pedestrian, for example. They have a unique characteristics, and like a detector that is like tuned for that would be better than other detectors. But even for our applications, we are doing tracking from broadcast feed, which is like a single camera. It's not multiple camera, and it has motion, and it has like additional things, additional occluders and things like that on the cameras that we don't have in the multi-camera setup. And in that sense, like definitely a generic tracker would assist. Not only that, we are like tracking different features. For example, all the key points of the court and all of these things. We are using deep learning in order now to get these points and to track them over time. It's definitely going into the direction of like of the VOT challenge.
Okay, so thank you. So now we are getting close to
Jerzy,
yeah?
sorry, there are some questions in the chat.
I don't see them. I don't see them. I was expecting people to raise their hand. Well, so my list of participants has occluded the chat. So thank you, Matej. So okay. Have there been considerations to add unusual objects such as transparent one for tracking? Yeah, like in my head, yes. You have also, like, for me, one of the ultimate unusual objects is a TV monitor that is displaying some feature film, which means that the appearance is changing all the time, which is being carried by someone else. I think it's a good point. Like, when does this become, look, you have to be careful so that you're, okay, it's a good point. So I will write transparent in my notes. What I mean, what is difficult here is that you don't want to go into real super special cases, like tracking a swarm of bees, which is like changing shape all the time. And is it an object anyway? Or you, so if we start getting like saturated, any of these special classes broaden the applicability. Okay, maybe it's a good idea. So of course we can do this in a soft way, that two sequences will be of in some way special objects, like transparent. Maybe, and Horesh said that, or someone in the talk, something highly like shiny surfaces, things which are mirror-like with lots of reflections. Yeah, that might be quite difficult. My son actually told me I would like to. He showed me a photo where a company car from some glass glass making company. It was a car which had a set of glasses on the side, and it was a perfect mirror. So it was showing all the other cars. I'm not sure whether it's even legal to drive such thing. Probably so shiny, mirror-like, transparent, point taken. So David Bondesson, would you like to? So if you are happy, just say I'm happy. Point taken, or you can comment on this.
Can you hear me?
Yes, yeah, perfect.
Great. Yeah, no, honestly, it's been one of those cases that we at our company in Germany have just considered a little bit, specifically for glass tracking. And it's just a problem that we consider a little bit. So we're still in the very early phases on it, but it's on the interest, and we've seen a little bit good data sets actually coming out from ICCV as well. You actually have one that's been curated for particularly transparent object tracking as well, or object detection. But so far we hadn't had really good results with it. So it's something that we have seen there is a need, at least from our side. And it's a little bit more general in that case.
Okay, good. So I will just say that you are probably aware, someone already mentioned this paper with Helmut Grabner, that when you are tracking real, like, transparent objects, you are often tracking something else which is connected to that. So if someone is tracking a piece of glass, often you track the person. And if we had to really only to track the changes maybe on intensity, it's very difficult. Okay, but good point. Fine.
Thanks, in any case.
Yeah. Okay, good. So we have another question here. Makalo says, according to the evaluation rules of VOT, a video will be divided into many anchors, and each anchor will be inferred separately. Well, it's too long evaluation time. So it's more like this. If we are tracking an object from a single frame, it becomes very important how the first frame looks like. And with these anchors, we are sort of saying we want to break this importance of the first frame. So for instance, if you are tracking a human face and the first frame in the video is always frontal, it's a very special case. Yeah. And you want multi-threaded toolkit. So Luka Chehovin, who is looking after the software, is here. He has,
yeah, hi.
He's probably the right guy to answer or comment on this.
Yeah, I can comment on this if you can hear me.
Yes, perfect.
Yeah, I mean, it's not. I mean, this would be very easy to do a couple of years ago when we only had like CPU to consider. But now, I mean, with GPUs, it's like then you need multiple GPUs to kind of basically assign for each basically instance, and so on. So it is possible, of course, but it would require then multiple GPUs for each of those runs. It would on a like large machine, it would probably speed up the entire thing and not sacrifice like then performance by switching between multiple runs. So I think this is what was like implied.
But what is important here in the Makalo's question is that speed and efficiency of benchmarking is also important. And maybe yes. we could verify how many anchors do we need to get a result which is statistically significant. Yeah? So we can see that if we just use one anchor at the beginning, it increases the variance of the results. Maybe we can use only 16 anchors and not 32. So maybe, and by the way, this is very much in the spirit of VOT, where we say there are two different things these days: large data sets for training. And there, if you have more data for training, that's better for you because you can always do a subset, but the more data, the better. For benchmarking, we are trying to have diverse, reasonably sized data so that the evaluation, the feedback is reasonably fast. So I think your question essentially says, make your evaluation fast and efficient because it saves times and energy and the carbon footprint. And the multi-threaded thing is like, okay, use the hardware more efficiently, but we can also maybe check when the trade-off between adding more anchors to stabilize the results and requiring more computation is doesn't mean that shows that more anchors don't help. So and we have probably set the number of anchors fairly ad hoc without any thoughts about optimality. So maybe we can look at that. Okay. So
Jiří, can I also add something to this?
Yeah, sure, of course. Go ahead, Matej.
So I think we've now had two comments related to the VOT toolkit. So one was this one, can we introduce multi-threading? And I think the other was, could you integrate other benchmarks into the toolkit? Now, I'm not sure if we've emphasized this a lot, but we would really like the community to actively participate in improving the toolkit as well. So one thing is suggesting to us, but we have limited work power, and we would be very happy if anybody would contribute to the code on the Git. Luca will check it, and we'll make the toolkit better for everyone together. So yeah.
Yeah. So it's, you can imagine that it's a quite large effort, especially on Ljubljana guys, Matej and Luca. So any help in terms of saying it would be nice when we say we will discuss it in the committee, say yes, you are right, go ahead, and if you can help us implement it, many thanks, hands clapping, and yeah, okay, fine. So thanks for the point, Matej. And I think that we have run out of the questions on chat. I think the session actually was useful. This is a reasonable number of suggestions, things to think of. So unless there are other points coming up, questions, which I don't see, I will close this feedback session. Thanks all those who participated, said something. I will hand over to Matej to have the final word. Closing remarks. In the politically correct language. Thank you. Bye.
Yeah. Thanks, Jiří. Yeah. So just to conclude. So first, I'd like to thank the VOT organization teams for their excellent work with executing all of the challenges. It's been a great deal of work, and the challenges were really executed well. I also like to thank the participants that are keeping the challenge highly relevant for the wider community, and because they're constantly attacking the performance bound and pushing it. So that's really great to see. I'd like to point out that it's been now 9 years since we started this challenge, and it's been amazing to see how much tracking has progressed during this time. And it's been really cool to measure this progression. So next year we'll have 10th anniversary. We'll be celebrating it hopefully at ECCV, if the workshop is accepted, of course. So I'd like to take this opportunity to invite you all to that workshop in Israel, and I hope to see you there in person. So thank you all. Thanks also to the invited speaker who delivered a very interesting talk for us. So yeah, thank you all, and see you next year. Bye-bye.
Thank you, Matej, for the organization. Thank you very much.
Thank you.
Bye.
Thank you.
Bye-bye.